Hello, good morning, sir.
Good morning, Surya.
Yeah. So we have only 15 participants joined now. So what do you suggest? Shall we wait for another few minutes
Yeah,
for the
no problem.
participants to join and
Yes,
then we
yes,
can start?
definitely.
Yeah.
So we can
Thank you,
wait
sir.
for another 5 minutes.
Okay, sir. Thank you.
So let me do one thing. Let me also grab a tea in the meantime. Okay. So I
Yeah,
will be back
sure,
in
sir.
another 2 or 3
Yeah.
minutes.
Okay, sir. Yeah, sir. Hello. Yeah, hello, Puneet sir. Yeah, hello, Puneet sir. Yeah,
Hi,
hello,
Fiza, I'm
Puneet
back.
sir.
Yes.
Yeah, okay. So shall I start?
Yes, 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 sure.
Okay. So good morning, all the speakers, coordinators, and participants. So today we'll be going to start with the 8th day of our program. And today's session will be delivered by Mr. Puneet Mittal. And Mr. Puneet Mittal is the founder of VLSI Expert Private Limited. He holds a BE degree in Electrical and Electronics from COER and Master of Electronics and Communication System from BITS Pilani, an MBA from Symbiosis Pune. He comes with a rich experience of 14 plus years in embedded semiconductor industry and has worked with biggest organizations in VLSI industry like Cadence, Synopsys, Magma, and LSI Logic. In VLSI field, Puneet's key expertise are static timings and analysis, PNR flow, methodology development with leading industry tools from Synopsys, Cadence, and Mentor. He is proficient in handling team, mentoring, project management, and customer engagement. He has been working for last 10 years to bridge the gap between the industry and the academia with the help of seminars, workshops, and skill development programs and guest lectures. He is also doing consultancy in education sector from school level to university level in terms of designing curriculum, training faculties, infrastructure building, advanced learning technique with technology. He has also been instrumental in skill development in VLSI domain for almost a decade through a dedicated online portal. He has created an online VLSI expert group in the semiconductor field through which he is interacting with several students, educational institutes, and universities. He is also associated with several social professional societies which are in education sectors like Youth Career Counseling and Employment Bureau and Indo-Canadian Innovation and Skill Development Center. He loves doing career counseling and mentoring to students. So with this brief introduction of Mr. Puneet Mittal, so we E&ICT Academy request sir to please start with the session.
Thank you. Thank you, Firoza.
Thank you, sir.
Good morning, everyone. So I know like you guys are not allowed to speak freely. So you are here. Most of you guys are on mute. But yes, I think we can use our chat box and we can discuss there. And yeah. So the way she introduced me, even I forget couple of things. They are like, okay, these were these were the part of my profile only. But yeah, I will try my best. So the topic which I'm going to discuss today is mostly on a PDK development, and as she pointed out about my degree point of view. So I have mixed background, like I have a electrical background, electrical electronics as a my engineering, then communication, uh, my master's, and working almost like 13, 14 years in a VLSI industry. And when I'm saying I'm working in a VLSI industry, so most of my experience is toward a PDK side, Foundry side, terms of the technology side. Worked with couple of companies on their power hungry devices, like how from the VLSI point of view, how the tool point of view, how the things are going to be different. And if you have noticed, I worked in a couple of EDA companies, and you know the job role of the ED companies, like what exactly those companies are doing. So those companies are basically coming up with the tools, and the tools for simulation, tools for layout, tools for everything. So these companies are trying to ease our work, and they are providing a environment to us, like okay, how to work on those particular tools. So what we are going to discuss today, we are going to discuss from that perspective. Like if we are going to do a circuit design, if from the device level to the so when we are talking about so device to circuit, and for the for a moment, let's forget about whether it's a 5G device, 5G related circuit, or it's some other thing. It's just a device to circuit. And yesterday, day before yesterday, the last 2 days, we had a good session, and in that session, we have discussed, we have seen about the devices point of view. And circuit side, like Ashish discussed before that, like okay, how you're going to design a circuit, how you're going to simulate that particular part. Now, the thing is, if you know a device and if you want to design a circuit, now how you're going to do that particular thing? Yeah, are you going to just do it straightforward, or you're going to do something else? So that something else, that's we are going to discuss today. Like, okay, what is the way we usually do all these things? So I'm going to discuss more in detail in terms of what is a PDK, why we are talking about the PDK development. So we will do step by step a couple of things. So as a agenda point of view, if you will see, I have just captured two agenda. One is a backup agenda. So in general, you will see people come up with the agenda like, okay, they will finish this particular part and then they are done. But in our case, it because depends on you guys. So if you're going to interact, then I will have less time. If you will not interact, then I will have more time. So that's the reason I have a backup agenda, and that in the agenda I have a backup thing, and then the packaging thing. So if the time permits, then we will discuss that particular part. If it looks to me like okay, uh, time is not there, we are done. So we will go as per the agenda of this particular session. That is like PDK development, and then a couple of uh, implementation technique in a semiconductor, the challenges, I would say, the challenges in the 5G implementation, uh, that particular part. So these are the two things majorly I'm going to cover today. And if time permits, then maybe we will discuss a couple of slides on the packaging side. Else we will skip those things. So in a PDK, first of all, you have to understand what is a PDK. And if we are talking about the content of a PDK. So let me just tell you what is a PDK. It's a process design kit. So now kit, so the word kit I'm talking about. So in that particular kit, all of you know very well, like a kit, that means there should be something inside that particular kit. So we are going to discuss those things like, okay, what something we are talking about, what is the different content of those those uh, the, the part of a kit, I would say. What is the importance of those things? So we will discuss in detail. That's the main goal. We will also discuss in terms of the quality checklist. We will also discuss in terms of the deliverables, like, okay, what are the different deliverables in terms of PDK. So if you are going to if you are going to design this particular kit, or I would say the prepare this particular kit, how you are going to deliver, or if you are receiving from someone, how you are going to receive that particular part. So that's from the deliverable point of view, we will discuss those things. So most of our time we will focus on this thing. Couple of examples I have. I will just show you like, okay, these are the things. Then after that, there are from the challenge 5G challenge point of view. I know this thing. Still, we have time. We can discuss those things. Few things we have already discussed in our previous session. But I just want to give you the perspective from the semiconductor point of view. Like, okay, from the semiconductor point of view, how things are related, and what are the different things you have to take care in terms of the designing, in terms of the challenge, from the uh, in terms of the techniques, I would say. So these are the two things. But before that, I would like to see like, okay, whether all of you guys are active or not. So think all of you guys have access of chat window. So if you guys can just say yes, no, just something, just drop a message there, so that it looks to me like, okay, all of you guys are active and mhm, not a single message.
So sorry for interactive. So the participants have the access of Q&A window, not the chat
Okay.
box, sir.
Okay. Thank you. Yeah. So in a Q&A window, they are sending message. Great. Thank you. Great. So okay. Thank you. I think that's great. You just corrected. Yeah. So good. So that means now in a Q&A thing, you can drop me a message. Good morning. Good morning, everyone. Great. So before I start, I would like to know from any one of you, what is your understanding from the PDK point of view? Anyone, just one line or a two line? Can you guys just let me know what is your understanding about the PDK? Apart from the uh, full form of a PDK, what do you think? What is a PDK? Anyone? No answer? Nothing. I think I at least someone should just drop a message like, okay, what exactly is a PDK? Mhm. Okay. Yeah. So you're saying it is related to the fabrication. If you're saying it is, say, basically having a P cells in the design rules, it's a tool. Okay. So if you're thinking it's a PDK is a tool, okay, and software where we can design models. Okay. Anyone else? It's good. Like, see, if you guys, if you people have confusion and if you don't know, that is good. Not a problem. Is then only the purpose of this program is like we are going to fulfill that particular purpose. If you guys know everything, then there is no point of having such program. So I always in any seminar in any I would say the workshop, I always uh, say to my listeners like, okay, it's good if there are different opinions. If good if you don't know, because if you don't know, then we will solve that particular part. So someone said it is a package of tools that is intended for the RF circuit design. Okay. Without PDK design can't communicate with the foundry. Okay. It is the thing which provide connection between the foundry and EDA tools. Okay, great. I think now we we all are going in the right direction in one way or other way. Now let me just uh, answer on the basis of your response. First of all, PDK is not a tool. Okay, so let me just correct you. It's not a tool. Yes, it's a process design kit. You're right. So process design kit. When we are talking about the process design kit, so in that we're talking about something related to the process, something related to the design, and that comes in a kit. It's just like in a package. So maybe someone can name it as a process design package, PDP, but somehow though someone just named as a process design kit as a PDK. So that's one thing. So it's not a tool, it's some data and something which is important from the process point of view. Now, what that process, we will discuss that what process we are talking about. So basically, from the fabrication process we are talking about. It's not like the process like okay, step one, step two, step three. It's basically uh, fabrication process. That's the one thing. Then the designing point of view, if you want to design something, then you need certain data. You need certain raw material, I would say. So that related to that, we are going to talk about like, okay, that's a composition, that's that particular part. And then yes, it's a package. Someone said like, okay, it is going to have a design rules, it will have a pieces. Yes, we will discuss that particular part. That's on the right direction. Yeah, software tools. It's not software and tools. Rule deck development. Yes, you are right. It is something related to the rule deck development, but it's not only the rule deck development. It has more than that. Is a thing which provide connection between the Foundry and the EDA tools. Yes, I think this is the almost the right definition, if you will say, from the process design kit point of view and fabrication process for design circuits. Yes. Now let's try to understand what is the PDK. What if we are talking about the PDK point of view? So what is our understanding? What is my understanding? Let me just tell you from my understanding point of view. So process design kit, fabrication process. your design, and then comes into a package. That's the process design kit. Now, what is inside that? It's a set of files used for the semiconductor industries. Now, when I'm talking about the semiconductor industries, so yes, so right now we are talking about this 5G devices fabricated in a certain wafer. So that's whenever you're going to use that fabrication related thing, that means we're talking about the semiconductor thing. So right now I'm just going to tell you the general thing, irrespective of the communication in terms of the 5G. I'm just talking about in terms of a procedure, because process design kit, because this is common everywhere, even it is for whether it is for the anything. It is basically, this term is related to the semiconductor industry to model a fabrication process for EDA tools. Now you have to understand, till now, like in the last 7 days, what all different things we have discussed. We have discussed in terms of circuit designing. Like, okay, for the 5G, what are the circuits we are going to design? How you are going to design that particular circuit? Now, in that particular circuit, if we are talking about the discrete component like resistor, we are talking about inductor, capacitor, we are talking about some other device basically. Now, how you're going to fabricate, how you're going to uh, do that particular thing, for that, there are going to be certain devices, right? So yesterday, day before yesterday, we have discussed in a very great detail about the devices, like FinFET side, in terms of gallium process, in terms of different stacks. We have discussed those particular things. So that means now we are talking from the foundry perspective, like, okay, how you're going to design, how you're going to, from the device point of view, how you're going to design those things. But the problem, I would not say the problem, but the next challenge is, let us suppose from the resistor point of view, if you are going to design a resistor with a certain specification as per your circuit requirement, now you have a resistor, but you want to check it whether that resistor, or take an example of a resistor or a inductor, if you want to do the simulation, or if you want to check it, like, okay, if this inductor, if I'm going to use this as a part of my circuit, whether my circuit is going to work properly or not. If I'm going to talk about in terms of a discrete component, if I'm talking about a board, like, okay, in this particular board, there is a circuit, and in that particular circuit, these are the different uh, inductor, these are the different resistor. So it's very easy for you to use that breadboard, or maybe some other type of a board where you can just solder it or just fix it and just see the response on the CRO, or maybe some waveform side. Maybe you can just give the input and you will see, like, okay, whether you're getting the output or not. So all this is basically the simulation, because that device, that circuit, or I would say the end product, that end product is not in the market. So what I'm just suggesting, if you have a discrete component, then you can just do the test and trial. So the breadboard, like in our college days, even now we are using in uh, like for the experimental purpose. If we are talking about the discrete component, then what you're going to do, you're going to insert all those components there, and then you can just do the uh, simulation in that's known as a simulation. Like, okay, I'm going to do the simulation, I will just check it whether I am getting the desired result or not. But obviously, here we are not talking about a discrete component, we are not talking about a bigger device. Here we are talking about a very small device. Here we are talking about a very small circuit. That circuit you are going to fabricate in a chip, and that's uh, yesterday we have discussed about MMIC, monolithic microwave IC. So here we are talking about an integrated IC. Here we are talking about the monolithic microwave IC. Now in that IC, if we want to check, like, okay, whether this component is going to work or not, how are we going to check it? Now this component, in the sense, inductor. So on a pen and a paper, maybe you came up and you said like, okay, with this specification, with this pictofarad, if you're talking about the capacitor, if with this thing, this particular ohm, my resistor, my capacitor, my inductor with this particular unit is going to work out. On a pan paper is okay. But actually after the fabrication, whether that is going to work or not, that we have to check it. So when I have used this word to model a fabrication process for the EDA tool, so how you are going to model it? So that is very important. So you have to understand from that perspective, like okay, if you want to model it, if you want to model a resistor, if you want to model a inductor, if you want to model a particular transistor. Yesterday we have discussed about certain FET related process. We were talking about certain fin related process. Now how you're going to model those things so that you can design your circuit using EDA tools, design tools. So EDA tools like Synopsys, Cadence, these companies, they provide a different EDA tools. So in those EDA tools, how you're going to design that particular capacitor, resistor, and how you're going to do the simulation. That is important. So for that particular part thing, now just try to visualize. There is a tool in that particular tool. You have just mentioned like okay, uh, second. So there was a tool you said like okay, this is my inductor. This is my basically the capacitor. So this is something which you did it like okay, and you said like okay, some 1 femtofarad. So on a pen paper, it looks very easy. Like, okay, this is a 1 femtofarad. Now you will say like, okay, the tool have a library in the left hand side. You can just drag and drop this capacitor will come, and then you can just say like, okay, this is a 1 femtofarad. Yes, you can do it. But think from the back end of this particular thing. Back end in the sense, what is going to be happen, how the tool is going to simulate it, what the tool is going to do with these different things. So that particular part that we are talking right now as a process design kit. So that's a part of a our uh, uh, process design kit. That's a part of our modeling related thing. So that's we are going to discuss like okay, what are the different components there. It is this thing if I do it. I remove. Just 1 second. Give me 1 second. Let me just close one window. Yeah, sure. So yes, so that's what I was just talking about. Like okay, this is we are going to fabricate. So this process design kit is basically the model of a fabrication process. Third thing which is very important, that is the specific to the Foundry's process variation. So now what is the Foundry process variation? So in real world there are two things. One is ideal process and another thing is a practical thing. So if you want to draw a line and if you're saying like okay, this line is a 5 centimeter. Now if I will ask you like okay, can you draw a 5 centimeter line 100% accurate? Then maybe you can say like yes, I can draw it. You are going to use a scale and then you're going to use a pen or the pencil and then you will say like okay, this is the 5 centimeter. But let us suppose if I will use a some lens, micro lens, and I will just use in that particular way. And then I can say, look, no, no, this is not a 5 centimeter. This is basically the 5.001 centimeter. So now when I have used this thing 5.001 centimeter, that means now we are talking about the significant digit, like how accurately I can design. So you can say, like, okay, that's okay. 0.001 is nothing compared to 5 centimeter. But if my process is a very small process, if you are talking about the millimeter waves, if you are talking about the microwaves. So if you will just talk in that particular way, then you can imagine, like, okay, what significant digit we are talking about. 10 to the power minus 3, 10 to the power minus 6. We usually talk in that particular way. So till that dimensions we are talking about, that means everything should be accurate till that dimensions. And then maybe they will say, like, okay, if it is a microwave we are talking about, so in a microwave, okay, then again there is a 10 to the power minus 3 significant is it we have to handle. We have to just check, like, okay, whether it's going to work or not. Now how accurately, how precisely my foundry are going to design a particular structure or a particular geometry, that is very important. So when I have mentioned the specific to the foundry process variation, so their process may have certain variations. So variations in the sense, if you are talking about a dimension of a 10 to the power minus 6, and they will say, like, okay, in our foundry, in our lab, like in a fabrication side, there can be a variation of plus minus 10%. Okay, so plus minus 10% is too much, maybe in that particular case. So at least you have to see, you as a engineer, you as a researcher, you have to understand, like, okay, whether those variations are going to impact my design, those variations are going to impact my output result or not. So let us suppose if you want to design a resistor or the capacitor with a 1 femtofarad, let us suppose the capacitor, if we are talking about 1 femtofarad, if you want to design, and then there is a variation of certain in terms of the uh, let me just tell you in terms of the formula, maybe then maybe uh, you can easily understand. So just layman language. So we have something C equals to epsilon A by D, and this D is basically the distance we are talking about. Now that particular okay. So are you guys able to see my screen, or it's just freeze up? Because at my case it is just showing is. Can anyone just let me know whether they can see my screen properly?
Yes, sir. So your screen is visible.
And whatever I'm drawing, that is also visible.
Sir, yeah. So you just started drawing something, I guess.
Yes, I did it last time also, but looks like
Yes,
okay.
sir. Last time one e equation was there, so it was visible.
Oh, it was visible. Okay, great.
Yeah.
Okay. So again, I'm just coming up with the same equation. C equals to epsilon A by D, and this particular D. Now you know if there is a slight variation. If I'm talking about this distance, I'm talking about this distance is basically between the two plates. Now, that particular distance, if we are talking about the 10% variation, and that particular 10% variation, that means 10%, I'm talking about the 10% of positive side, 10% of this D. So if we will talk in that particular way, like, okay, this is a 10% of D, that means now we are increasing the distance. Now, if we are going to increase the distance, it is going to definitely change your capacitor. And if it is going to change your capacitor, then in your model, in your circuit, your output is going to be change what percent, and if it is going to change, whether that's your circuit is susceptible for that particular change or not. And if that is your answer is yes, that is not going to affect my end result, then there is no problem. But here I'm assuming, like, okay, you have already taken care, you have already checked all these things. And how you're going to check it when the founder is going to tell you, like, okay, this is the process variation I'm talking about right now. So those things, that means as a part of a PDK, if we are talking about, like, okay, uh, with respect to the foundry, they are going to tell me all these details. That means someone need to tell you, like, okay, this is the variation, and what that who's that someone? That someone is a foundry where exactly you're going to fabricate all these things. So that's the process variation we are talking about right now. And then obviously uh, once everything is done, then only you can design a MMIC, monolithic microwave integrated circuit. Then only after that you can say, like, okay, everything is good. So if I will talk about created by the foundry defining to the certain technology variation for their process, yes, foundry usually create these PDK because they know their process very well, and they will come up with a certain variation related thing. Customer may enhance the PDK. Now, customer as a you, if you are going to use those PDK as it is, but you want to make certain changes. And what does it mean? So, in a PDK, if it is a process, if it is a foundry specific, how much you can change it? No. So, when I'm saying the change it, you cannot change all the parameters, but there are few parameters which you can change as per the tool requirement, as per the design requirement. Like, they came up, the foundry came up and they said, like, okay, in their design kit, they came up with the 10 different type of devices, but you need a another 10 different type of devices. And foundry is giving you the flexibility, like, okay, these are the things which you can change at your end, like, from the parameter point of view. That means you can make certain changes in those PDK. Like, okay, these changes if I will do, then it is going to be good for you. Then what is going to be happen? Designers are going to use those PDK. They are going to simulate it. They are going to draw the different circuits, and then they are going to verify their design. That's the role of a particular designer. Like, okay, now I'm going to use it as it is. And then once everything is good, then you will say, like, okay, or the designer is going to say, like, okay, I have simulated this thing and now everything is good. Now you can hand over to the fabrication team so that our end product is ready. That's basically the complete process. So in that particular process, I'm just again reiterating in a different way. So in our journey from the last 7 days, think in this way. Now you are designing a circuit. In that particular circuit, there are different components. In that particular component, now you want to design those component on a particular chip. So then you came up with the uh, you have seen the devices side. Then you figure out, like, okay, this particular component I can design using this particular technology. So whether it is a capacitor, it's a resistor, it is an inductor, or it's a particular gate, you came up like, okay, this is the way I can design this particular part. Now you want to fabricate those things. But before fabricating, because fabrication is just something like once you will just go to the TSMC or SMC and you will say, like, okay, I want to fabricate this particular chip. Then they will say like, okay, no problem. Have you verified everything? And then if you will say like, yes, we have verified everything, then they will just fabricate the process, because they don't they they are not going to question in terms of your circuit whether your circuit is going to work or not. They will just say like, okay, if you verified everything, then we are okay. We are not responsible whether your circuit is going to work at the end of the day or not. So the moment they will say like, okay, we are not responsible whether your circuit is going to work or not, then you will say like, okay, how much is the cost? And then the moment they will say it's going to take a big amount, maybe like 10, 20 lakhs rupees, if they come up, then you will say like, okay, no, that's not possible. Even let us suppose if someone will come and they will say like, okay, it is a 2 lakh rupees for a one test chip. And for that we have to see like, okay, whether the other processes are there or not. Then again, that amount itself is a huge amount. Then you will say like, okay, let me re-verify, and what are your parameters on which we should verify this particular part. Then they will say like, okay, see, my foundry have certain variations, so these are the rules. You just check it on your side, and which then you will say like, okay, on which particular tool we can verify. Then they will say like, okay, our PDK, our process design kit is verified with respect to, let us suppose, the cadence tool or maybe the synopsis tool. Then you will go back and you will see like, okay, you have used the open source tools, okay, and somehow these particular foundries saying like, okay, they are not verified this particular open source tool. Then maybe I have to just check it like a cadence or synopsis, or maybe you can ask them like, okay, are your PDK is compatible with these open source tools or not? And once they will say yes, then you will just go back. You will just see like, okay, it's the same tool you're talking about. Then in that particular tool, you're going to use those those models. Now that's the second line. If you will see, you're going to use that particular model. You're going to create a circuit, and you're going to do the again. You're going to do the testing as per the provided data. Now, what data we are talking about? Till now we were talking about the process, like, okay, this is the way we use the PDK, but what data we are talking about? So we are talking about the primitive device library. So in the PDK, there going to be primitive device library. That means it will have a symbols, it will have a device parameters, the p cells, like someone just mentioned, like the p cells will be there. Yes, parametric cells will be there. Now that parametric cells, in the sense, there are certain parameters which you can change, but that's cells are there. You can use it as it is, and that's replica of your uh, cells of your discrete component, I would say. So that's basically you're going to create a circuit. So with the help of these primitive devices, the library, you will just drag, drop, and then you're going to make certain changes in with respect to their parameters. The moment you're going to make certain changes in their parameters, that means when the tool is going to simulate, that's basically the tool can simulate. Tool can understand those parameters. So like you are saying length is equal length. Let us suppose you just change up one of the parameter, which is a length. The moment you will change the length, that means now we are talking about a different inductor with a different length. Now those length you will change. Obviously, your inductor value is going to change, but how that inductor value will be there, that's a responsibility of the tool, how they're going to calculate that particular part. So that's basically in terms of the primitive device part. Then after that, I have also mentioned like, okay, once things are done, there are certain verification you have to do in terms of the foundry. Like, so foundry can say, the fabrication company, they can say like, okay, if if you will come up with these dimension, I cannot fabricate. That's the one thing. Or they will say like, okay, we have certain rules in terms of like, if your dimension is less than this, then we cannot give you the guarantee, like, okay, whether you will get the right result or not. So what you're going to do, you will say like, okay, if I have to work with this particular foundry, then what I'm going to do, I'm going to I should verify my circuit with respect to that particular uh, those particular rules. So what Foundry is doing, they are going to give you the deck. They are going to give you the certain decks. So like I have just mentioned the design rule. So how you're going to design it, they will give you that particular part. So once they will give you those rules, you will make sure you just follow those particular rules. And how you're going to follow those particular rules, you're going to do the certain verification. And that's the reason here I have mentioned it's a verification deck. That means these are the decks which you have to verify. These are the decks you have to follow. Once you will follow, you are going to design it, and then you have to verify it, like okay, whether it is working properly as per the Foundry recommendation or as per the Foundry rules. So that's a part of a verification side. Now, when I'm talking about the designing, like you're going to design certain things. So now, what is the meaning of it designing? So yesterday we have discussed like, okay, they are going to be the source, they're going to the drain, they are going to be the different layers. And that's what the Foundry is telling you. Like, okay, we can talk about the different layers, and we can talk about the different stacks. Now, how the Foundry is going to provide you that particular data, like, okay, I am supporting my Foundry is compatible with respect to the four different type of layers. We are uh, we are compatible in terms of metal 1, metal 2, substrate, the this dielectric 1, dielectric 2. So if you will say like, okay, between the two capacitor plate I need a dielectric of some other constant. So then if the Foundry is not uh, compatible, they cannot do that particular part, then you cannot ask them like, okay, that no, I need this particular dielectric only. And if you will ask them, then they will say like, okay, we have to change the whole process, then you have to pay extra. But this is the process, this is a dielectric which most of the people they are asking us, and that's the reason that this is a low cost dielectric. Now it depends on you, like, okay, how much you are ready to invest. So if you say like, okay, this is a dielectric with this specific uh, uh, material, so you just use it, and that's the only dielectric which is going to solve my problem. Then you have to just talk to the Foundry. But if Foundries have a certain predefined dielectric constants, that particular dielectric, then you have to follow those things. So the question come, how you will come to know. So Foundry is going to provide you these information as a part of a technology data. Like, okay, this is a technology I'm talking about, and in this particular technology, this is going to be my different layers. This is going to be my different dielectrics. Now that layers, that dielectric, this can be generic, this can be specific to you, depending upon your requirement, depending upon the rest of the people requirement. And that's the reason, if you will see, there are different foundries. There are few companies, they have their specific their own foundries. Most of the research institutes, they have a, even though maybe they have a very small, but they have a very small fabrication unit. And in that fabrication unit, they usually do these type of experiments, like, okay, if I'm going to use this particular dielectric, then what's going to be the result? If I'm going to use this particular dielectric, then what's going to be the result? And once that is done, they're going to provide you like, okay, if it is a some layer with the this particular some layer with this particular material, then what is the complexity, what is the result? So all those research, they are going to do it. Once that is done, then they are going to create, if they want to produce the component, they want to ready, like, okay, uh, I'm ready to fabricate it, then that is going to be the part of a PDK. So in the technology data, you will see there is a layer number, the purpose, and all other things will be there. Then, like, if you remember, I have mentioned, you are going to ask your Foundry, like, okay, this PDK is compatible with this particular tool or not. So what does that means? The moment you're going to use a tool, they will say like, okay, tell me which technology node, give me the technology data, and then they will give you the certain technology data. Sorry, then you will give certain technology data. So the moment you will give a certain technology data, then if there is a tie up in the sense, if there is a the agreement signed between those tools and the foundry, or if your PDK is compatible with that particular EDA tool. So what happen? They sometimes they come up with a default color schemes. They will say like, okay, the moment you are going to pull this particular technology data, metal 1 is going to be in a blue color, metal 2 is going to be the light blue, metal 3 is going to be light blue but with a check. So that as a end user, you can easily figure out like, okay, we are talking about the metal 1, metal 2, metal 3. So I will show you one small snapshot where the tool interface and is going to be very easy for you to understand like, okay, what exactly you're designing. Think in this way, like if everything is going to the blue color, metal 1, metal 2, even the diffusion, even your drain, like the substrate, or all the every layer is a blue color. It's very difficult for you to design anything. So like in a paper pen, we if there are two ways, you use a multicolor pen, or maybe you just draw everything with the black and white, like in a pencil or something. So if there is a complex diagram and everything is um, a single color, then it's very difficult for you to figure out like, okay, whether the two layers are on the top of each other, whether they are overlapping, because now we are not talking about the 3D model, we are talking about the 2D model. So this color, fills, display attribute, all these things is basically related to the tool, but it's not related to the foundry, because for the foundry things are different. They come up with a some GDS number, like, okay, this is going to be my GDS number. So they usually talk in terms of the GDS. So that's a different topic of discussion. But from the tool point of view, things are going to be in the colored fashion, so that from the pictorial point of view, you can easily visualize like, okay, which is a metal one, which is a metal two. So in the technology data, you will see all these particular part. There are certain electrical rules also, there are certain process constraints also, like I have just mentioned in terms of the process variation, like plus minus 10% variation. So then you will see in the technology data, they will mention very clearly, like for uh, metal one, my process variation is going to be this thing. Now process variation in the sense, width is going to be vary with this much of percentage, and if the width is going to be vary, whether my space has any dependency over the width or not. So all those interdependent parameter relationship is also the part of your technology data. So like in the lower technology node, just to give an example, there is width and the thickness dependent spacing. So that means if the width of your a particular wire, that is going to change, and your thickness is going to change, your space is going to change. So that means there are two parameters. If those are going to change, how the space are going to change. So it's not like, so it's basically we are talking about the complexity of my design. So it's not like, okay, width can change only independently, space can independently change, and the thickness can independently change. So that's good if everything is independent, but we know, so everything is not interdependent. So they have certain dependency. So, but that's the that's the role, that's the job of a foundry, that they should tell you like, okay, these three parameters are dependent with each other, and this is a relationship of their dependency. Because the moment they will tell you like, okay, this is a dependency, then you as a end user, you can model it. You can just do the checking on your side. If this is a dependency, even in the worst case, whether my circuit is going to give me the correct output or not. So that's basically the part of that's basically the importance of this particular technology data. Then we are talking about certain rule files like in a tool dependent rule format. So now we are talking in terms of technology data verification. Then we are talking about the primitive libraries. Now, from the tool perspective, maybe the tool can understand a particular language. So, tool can understand a particular language in the sense when I'm saying the language is basically the format, because every tool they have their own proprietary thing like, okay, I can understand this particular format. Now that particular format, if Foundry is going to give you a, so Foundry has a different options. They will say like, okay, I will give you the general format. That is my format. Now you have to talk to the synopsis, cadence, and they are going to provide you a their respective format. And why their respective format files are important, because that's help that particular tool from the runtime point of view, and their tool may can understand in a particular language. So yes, it's going to be the English language, but still, like when we are communicating with each other, everything is in English. But maybe when you two, maybe someone from different country, if they want to communicate with each other, then they can use their own language. Now, here we are talking about the global thing. TSMC, the Taiwan based, and Global Foundry is a US based. So they say they and then the synopsis and then the cadence, and they came up and they said like, okay, my tool can understand this particular format. It should be written in the English language, but the width of a particular layer supposed to be written as a WIDTH width. Maybe the other EDA vendor, they will say like, you know, somehow my tool is written as a uh, W. So wherever is written as a W, I will consider that as a width of that particular layer. Then there is a third, there is the IEEE standard. And in that particular IEEE standard, maybe every tool is ready to understand that particular part. So, but the question is right now there, I'm talking about the three different formats. One is the IEEE standard, one is the vendor specific, and the third is a foundry specific. So that means the rule files, though those tool dependent format files, certain data suppose is going to be with respect to out of these three different things. So that's one of the data of our PDK. Then the next one is in terms of a simulation model of a primitive devices. Now, when we are talking about the simulation model of a primitive devices, now think in this, so let me tell you from the yesterday example. Yesterday we were talking about a FET, we were talking about a source and the drain, we are talking about the fence, we are talking about the um, uh, certain layers, and those dimensions we have also talked about like, okay, there are certain dimensions are going to be there. Now you have two options. Either you just do everything your own, you draw everything, you design everything. I'm talking about the device. I'm not talking about the circuit now. So from the device point of view, you design each and every layer. Once you will design each and every layer, and then after that, what you can do the simulation. You can do certain simulation in terms of you just run it and just see it. What is going to be my the output waveform? That's the one way. Second way is you just pick those capacitor, resistor, transistor as it is. And those resistor, capacitor, transistor, those are already simulated by someone. Forget about who's that someone. Someone already simulated that particular part. And they said like, okay, from the fabrication point of view, this is something which we have simulated for you with a certain default values, but they are going to provide you a option to change certain values. And those certain value, the moment you're going to change those certain values, you will get the another number. For example, C equals to epsilon A by D. Now in this C equals to epsilon A by D, epsilon is something which is a dielectric constant. And you know, as a designer, dielectric constant is not in your control because that is something the foundry specific. So if it is a something is a foundry specific, so what people can do, they can say like, okay, this is the this dielectric constant is fixed. You designer cannot change this particular dielectric constant. They can change width, length, and distance. Now distance. Now when it comes to the distance, maybe you may foundry is saying like you cannot change the distance directly. It is going to be the certain multiples. That means again they're going to be a base value and then going to be a multiplying factor. And then you can multiply with that particular factor. So all these things they are going to provide you. Someone is going to provide you. That means I'm creating a model for you. So in your practical class where you are just taking an idle component, and in the idle component you are making certain changes there, and those changes which I'm talking about, certain numbers which are going to change, that number is a user editable. Rest of the numbers in the backend side, that's something which even you maybe you don't know. But with those numbers only you can come up with the certain results. So that's basically the simulated model. That's the reason I have mentioned very clearly it's a simulated model of primitive devices. Someone already simulated and that is already present. Now what you have to do, you have to just drag and drop, and you have to use it as it is. If you want to make certain changes there, you just do certain changes because you don't want to design it from the scratch, because that's you're gonna do it each and everything your own. So if someone is going to provide you certain models of capacitor, it's very easy for you to design it, and you come up with a circuit designing, and that's what you're doing right now in your tool. You're just using the as it is model, and then you're making certain changes there. So that's I'm talking about as a part of a PDK. So that's also Foundry provide just to ease your work. So um, that's basically the simulated model. And the last one is a design rule manual. Now, till this, all these things, I'm talking in terms of the files where you have to open those files, and those files we are going to use it. But there are certain way the Foundry is going to communicate with you. That's the textual thing. Textual in the sense the document I'm talking about in terms of the PDF. Like, okay, these are the things which is part of your PDK for this particular process. These are the different models. And if you want to make certain changes, you have to make these changes. So I'm talking about in terms of like the documentation. Obviously, that's is also required right now. If they are going to make certain changes in the PDK, then they're going to the PDK version. And then they are going to mention it like, okay, this particular version has these particular features. This particular version has these particular changes. So that's going to be the part of your design rule manual. So that's the manual representation will be there. Okay, before I will just move, let me just check it if any one of you have any question. Yes, so I think someone just asked, will PDK be the different for a device to be packaged in a gold or the silver metal for wearable electronics embedded jewelry? Okay, so Vijay, uh, short answer is I'm just dividing your question into the three different parts. One is electronics embedded jewelry you're talking about, wearable electronics embedded jewelry. So this is a part which is related to the end circuit. This is the part which this is something related to the end product. And when we are talking about the PDK, so PDK is related to the process. is related to the a particular technology node. Now, using that particular thing, what circuit you are going to make, that's something is up to you. So if those components, those models, so right now, I can just tell you like in front of you, there are the six different boxes. Within these six different boxes, there are different different material or the different uh, things which is a part of a PDK. Now you can use anything. You can create your own circuit with respect to that particular circuit. Maybe you can come you can say like, okay, this is the end product is something related to the electronics embeddable jewelry, or maybe you can say like, okay, it is not a jewelry. It's basically some showpiece. So that's basically the end product. So I'm not talking right now in terms of the end product. Yes, end product maybe if you will say, let's say there is a mobile phone and for design as a 45 nanometer technology or the 32 or maybe 28, then the answer is yes, because now you have used a word like a technology dependency. So if you are not using the technology dependency, then it's okay. um, uh, it can be a PDK independent. Now, the second part of your the question is package in a gold and a silver metal. So again, you're talking about the gold and the silver. Now, this gold and the silver is basically if you're talking about the external gold and the silver. So again, how you're going to do the packaging, it doesn't matter for me. So yes, from the noise and all other things, those things matters. But again, if it is the external part, then it's okay. So from the inside, you have to design the circuit in that particular way. You have to verify whether it's going to work or not. When it comes to the first part of your question, PDK will be different for the device to be packaged. So for the PDK is different for the device to be the package. So now, these devices which you're talking about, so from your question, it looks to me you're talking about the devices, the external, the end product which you're talking about. But if it is something related to just in case if you're talking about the devices which you're going to use inside the your IC, and if you want to make certain changes there, then yes, your PDK is going to be different. Make sense, Vijay? Okay. What about others? Any question? Any one of you? No questions? If you have no questions, can you just guy just type it and say no questions? I just need to know whether you are able to understand what I'm just trying to deliver right now. So I can't see how many of you are active, how many of you are not active. So you guys are active? Yes or no? Okay, no idea. Okay, so let me continue. If you guys are active, then it's good. So now we are talking about till now as a different the PDK thing. Now we are going to talk about certain examples of the PDK, like okay, what is the way things are defined and what exactly you can change it. So in your, I just took an example of like NMOS circuit. Now here you can see there are certain symbols. This is basically the symbol. Now in this particular symbol, it's not like four or five, six, seven lines. It's not just the lines. Basically, this is just a representation. That's what we have mentioned. There are going to be the certain symbols are there. So this is the part of a symbol. Now, when it comes to the parameters, so these are the certain parameters, and this is a default parameter right now. But you can make certain changes here. So certain parameters are editable parameters. And then if you will see, if you will just open the file, if you will see like okay how things are defined, whether I'm saying okay what is the capacitance of source to drain, what is the what is the capacitance between gate to drain, and all these things, what is the length. So in this particular symbol, what exactly we are talking about in terms of the length, or we are talking about in terms of the inductor capacitance, all other things, like okay how the tool is going to understand all those things. So that, so you here you can see everything is as a it's written in a textual format. It's just like you should know, you should be able to understand like okay what is written there. If you're not able to understand this particular part, obviously the tool should be able to understand like okay what is written there. I'm taking another example. Here you can see it's I'm just trying to show you the mutual inductor. So there are the primary winding, secondary winding. There may be certain L1, L2, and then you can talk about like okay, which is a positive, negative. So these are the things which you are using day in, day out when you are going to do the circuit designing. Now, in this particular circuit design, there are certain parameters which you can change it. So this is as such as a part of a transformer we are using, but obviously this particular transformer, if you want to fabricate in a particular chip, then what you have to do first, you have to make sure like okay whatever the fabrication you're going to do it, that particular fabrication is going to work properly or not. So on a paper pen you came up and you said like okay this is the fabrication, this is the transformer we need. Now in that particular thing you can talk to the foundry, or even if you want to come up with a uh, creating a PDK, then you should know like okay how you're going to model that particular part. So first you have to calculate all the dependency, what is the output. So here you can see even the relationship we are also talking about, like okay what is going to be the pass, what voltage you're going to apply here, what signal you're going to apply here. On the basis of that, this is going to be my we can say the equation, the output equation, and accordingly your tool is going to do the calculation. Simple example for the one of the uh, inductor. Now in this particular inductor, there are certain default values, and then we have these parameters. That means these parameters you can change it. Now if you talk if I will talk about what are these parameters, so like if you are talking about L, here we are talking about inductance, TC1, TC2, temperature coefficient, d temp, difference between the inductor and the circuit temperature. So now all these things when we are going to do the modeling. So yesterday also we talked about a little bit about the modeling part, like okay the small signal, we are going to talk about we discussed yesterday in terms of the small signal model, the large signal model. So those what does that mean, the model? So that model in the sense it's not just like okay there is a physical device, and in that particular physical device how you're going to do the mathematical calculation, and for that we came up with a certain model. Now from the tool point of view, how you're going to represent that modeling thing. So from the tool point of view, if you want to do any MATLAB simulation, or if you want to just do certain simulation, so what you're going to do, you're going to write all those parameters, and then you will say like okay this is the equation we are talking about. And that equation, so the advantage of using the tools in a ED tools, if you will say, that equation they have already built in. That means those equations are already as a part of their process, as a part of their tool. And it's not like the simple equation, even the complex equations are already the part of that. Now, in those complex equations, you have to provide the variables, the values of all those variables, like equation we have discussed yesterday. So those values to those variables, how you're going to provide it? Are you going to provide it just a keyboard and just say like, okay, this is the thing? No. So what you're going to do, you're going to write a file, and in that particular file, you will just list down all those variables. Then you will say like, okay, this is the TC1, this is the TC2. So like here, TC1, TC2, D temp, R, scaling factor. So you just write all those parameters. In front, in next to those parameters, you're going to write certain numbers. And what the tool is going to do, tool is going to read that particular file and do the calculation. Now, out of those parameters, like I said, there are going to be the certain parameters which you can edit. So in this particular window, maybe you will get certain editable parameters. And now you can just click it there and you can just change it. That means now what the tool is going to do, it will read the by default all the parameters which is present in that particular file. And then it will read this particular data which you have manually entered, and it will do the simulation. So that's basically we are doing now. That particular file, which is a template which you have created as a file, there, if it is just a matter of 2 or 3 or 4 parameters, then it's very easy for you just to write that particular file. But if I will talk about like, okay, that particular file has around 200 different parameters, 200 different variables, then it's going to be very difficult for you just to write it. Or even if you are ready to write it, then maybe you have to, you should know all those variables, all the values of all those variables. So what PDK, in a PDK, what we are doing, we are talking about those particular values only. Like, okay, if those values has a dependency on the process, the fabrication, they are going to provide you that particular thing. If there is something which has a dependency over the design, you are going to provide that particular part. If there is something which is which has a dependency over the tool or the technology, Foundry is going to provide you those particular parameter. And when I'm talking about in terms of the compatibility with the tool, so it's the same thing. Like, okay, if there are 400 parameters, if there are 500 parameters, now your tool is not compatible. That tool cannot read all those 400 parameters. Let us suppose the tool can read only 20 parameters. So then there is no need to provide such type of PDK where there are around 400 variables. Second, maybe the way you have mentioned the parameters, you said like, okay, TC1, TC2 is the temperature coefficient, but the tool is not able to understand the TC1, TC2. That's what we have discussed about in terms of the temperature coefficient. So like here you can see in case of a MOSFET, so there are lots and lots of parameters are there, and those calculations are there. These are something which is editable one, and whatever be their calculations, which is a false, which is a what is going to be the width, what is going to be the number of fingers, all those things is going to the part of that. Similarly for the resistor also. So I'm just giving an example, like, okay, these are the many things, these are the things like which is just behind each and every component, and that and on the basis of that only our the tool is going to work, and it is going to basically do the simulation. Now the pieces, someone talked about the pieces, what is there in the pieces. So in the pieces, we are also talking about in terms of till this particular level, like, okay, this is the layout we are talking about. We are also talking about in terms of the dimension. So here, if you will see in the fine print, it is written the box 0.02, 0.19 WNL. Now here we are talking about the way the layers are there. So in the form of a box, this is going to be my width, this is going to be my length. In this particular way, everything is written. So here you can see in the pixel there are two things. One is in terms of the layout, which you can see it, and there is another is a this particular format which you can read also. So you can see, you can visualize, and you can read that particular part. Now here, if you will see, this particular instance, this particular portion, then it is just telling you like, okay, what library we are talking about. So we usually use the word the library if we are talking about a specific technology node, the pieces. Then what type of cell it is, then what is the position, what is the rotation, all this from the geometry point of view. And then there are certain parametric windows also. Like, okay, this parametric cell is has this, what is the W, L, and G. So this is the thing. Now these pieces with the different dimensions are there, and you can just use those pieces directly in your design if it works, if it suits to you. This is the part of DRC rule deck. So when I was just talking about like, okay, there are going to be a certain verification thing. In that particular verification, I just took it. This is one of the thing, like DRC rule deck, how Foundry is going to provide you the different Foundry rule deck. So if I will talk about in terms of the Foundries, and I just mentioned like Foundry is going that anything they can provide in the two or the three different way. One is the documentation. So these design rules Foundry can provide you as a part of a document, also as a PDF, where all the pictures are there, and they will just tell you like, okay, you just follow this particular part. Now that is basically the documentation, the PDF document. Now when it comes from the synopsis and the cadence point of view, they will come up their own deck. They will come up with their own uh, tools. So they have their own tool to do this checking, and their tool may have their own language or the format, and that particular format, that particular language, maybe the synopsis and the cadence, they are going to, it's not maybe, they usually write those decks. So Synopsys has a different team, they write it. Cadence has a different team, they write it. And they, once they will write it, then obviously you have to use those particular deck. Now, what usually happen, the way the different organization works, so the Synopsys write it, and they will also talk to the foundries, and they will say like, okay, uh, on the as per our understanding of your the PDF document, we have created this particular DRC deck, design rule checking deck. So this is the deck which we have created as per our understanding of your PDF. Can you just verify once? And now if they verify it, then they will say like, okay, this particular deck is verified with from this particular foundry. So as an end user, as a you, it is very easy for you to make sure like, okay, everything is in sync. Whatever the synopsis is providing, whatever the TSMC is providing, these people are in sync with each other. It's not like I have to create the deck as per the synopsis tool. So that's what is this particular format, and this the part like, okay, how things are uh, sync up between the two organizations. So similarly for all other all other verification decks also. So like in a verification LVS side also they are going to provide you, and then as a end user, once you're going to use their tool, if you will face certain problems, then it will tell you like, okay, what issues are there. So this is a part of a this is basically the part of a the output of the LBS file. So once you're going to run it, then you will get certain these things. So what is matching, what models you're talking about, whether this model is matching with your layout or not. And so it is going to tell you in terms of your circuit, whether your circuit uh, on the device level, if we will talk about from the fabrication level, whether it is you have created the same circuit, the layout of the same circuit or not. So that's basically the layout part. Then some extraction rules. So yesterday we have discussed about like, okay, you have to extract, you have to do the parasitic extraction. So now you are ready to do the certain parasitic extraction. So like, but those parasitic extraction for the complete designs, but from the on the device level also, yesterday we discussed like, okay, if you have to do certain device level extractions, then if there is a already simulated cell is there, then obviously you may be expecting the same thing like, okay, if the device is there, if I'm going to use the same device, then whatever the internal parasitics, internal capacitance, everything supposed to be done by someone else. Why should I do that particular part? If they are doing certain things, they should give me the complete details. So this is basically the is basically for a particular cell, they are going to provide you the extracted basically the data in this particular format. This is a technology data which I was just talking about. You remember layers I was just talking about. So here you can see there are the different layers, the different color schemes as per the vendors. So this is the color. Obviously, this is not the requirement of a foundry, but this is a requirement of the EDA vendors, and that EDA vendor they came up with this. But so you just so EDA vendor is going to talk with the foundry, and they will say like, okay, this is the blue color, this is the red color. Now, I'm not saying you cannot change it. Yes, you can change it. That's the customization which you can do on the tool level. So most of the tool, they're going to be certain pencil drawn is here, or with the right click, change the color of your layer. You can make all those changes. So this is basically the color part. Now here again, this is a nomenclature. So now here you can see it's written PW. What is it? So NW. What is the NW? As such, if I will ask like, what is the NW? So it's basically the some uh, naming convention, I would say. So maybe you can use this as a NW. Basically, it's an anvil. I know this particular part that okay, this is a anvil we are talking about. So this is M3 is basically the metal three. VR1 is a VR1. So these nomenclature, I would say, naming convention, I'm able to understand. But how but think this is not a IEEE standard. It is basically from the tool perspective, from the designer perspective, maybe the foundry perspective. So what is going to be happen like maybe the tool is saying NW is as a annual, and the foundry is saying like, okay, I don't understand the naming convention like this. For me, it is a 132 layer number. You will say like, okay, I need to say like, okay, annual, NW, annual. So now we are talking about the different naming conventions. So those naming conventions supposed to be mapped with each other. So there is a one more file which is a mapping file that's part of a technology data. So you will get a mapping file where everything is mapped with each other. So that's going to be there, and it's going to be written as a part of a technology data. So like you can see just a snapshot they have mentioned like, okay, what is a unit, what shapes we are talking about. If we are talking about the wires, what angles, what type of the joint and is going to be there, what is the color scheme, what is the GDS number. So here you can see the GDS number is 02. What is the data type? Is 0. So for a particular wire, for a particular technology, you will get these type of technology files. So very small technology file data is too big. It's basically it will have the layer specific each and everything. Remember, this is not a design specific. I'm talking about from the layer specific. So if in your for a particular technology, if we are talking about a particular stack, if let us suppose 8 metal is stack, 5 metal is stack. So for those eight metal, 5 metal, they are going to the two different technology, and in two different technology files. In one technology file, you will have all the data with respect to the 8 metal stack. In another technology file, you will have data with respect to the 5 metal stack. So that's basically the part of the technology file. This is the same thing which I was just talking in terms of the different parameters. Here you can see there are different parameters. When I'm saying the different parameters, so for the N1 MOS model, you can see these parameters are there, and these some default values are also there. So right now, this is a based on your equations, like which equation you want to use, whether you want to use the very common basic equation, and on the basis of that particular equation, maybe you will have the BSIM1 model is more than sufficient. I think BSIM1 may, if I remember correctly, it has, I think, 6 or 7 different parameters. Then there is BSIM2, 3, 4. 4, I think it is 64 or no, not the 64, it's more than that. So on the basis of the number of variables, things are there. So like here you can see for the uh, PMOS, these different um, variables are there for a single PMOS model. So for the PMOS model, these are the things. So here you can see like we have defined each and everything in terms of TOX, in terms of your uh, threshold voltage, in terms of your lambda, which we are talking about, in terms of your capacitance also, the diode also. So we are talking about like, okay, everything. So all these parameters, when you're going to do certain simulation, so in that particular simulation, the tool is going to use one equation, and for that particular equation, these are going to be the parameters. So this is a part of a PMOS spice model. This is what I was just talking about. So this is just for the PMOS. Similarly, you will have a for the different inductor, capacitor also. And now, if there are 10 different type of inductor, and then all the 10 different type of inductor will have a 10 different model files. Okay, so now we before move to the next section, let me see if any one of you have any question. Do you guys have any question? No questions. That is long back. Now what about now? So this is basically all about the content of a PDK. Like, okay, what is present inside the PDK. Now, what we have to discuss, we are going to discuss in terms of uh, from the documentation point of view, what are the different things you have to document. Now, if you have to create a PDK tomorrow, if you have to create a PDK, then in that particular PDK, what are the different things you have to take care from the deliverable point of view, from the documentation point of view. So we are going to discuss a little bit about that particular part. So I'm just waiting. Either you just say no questions, or you just, if you have any questions, just ask those questions. Okay, looks like today people don't have much questions. Am I right? Or maybe you guys are not able to understand it. That may be one of the reason. Is it a very boring session, or is basically a very something like uh, you're not able to understand it? What is the scenario, guys? It just looks to me like, okay, I'm just speaking in front of what is that, in front of a laptop. Okay, someone just said something. Okay, so understanding, okay. I don't know. Another someone is saying, is there is fabrication difficulty associated with the graded junction? So if I pronounce your name correctly, your name is Sri Lakshmi. So Sri Lakshmi, simple answer, because this question is very wide question. Simple answer: there is no fabrication process where there is no difficulty. So that means every fabrication process have their own challenges. So like in terms of whether it is a see here you're talking about in terms of a graded junctions. I'm just saying like graded junctions have a lot of challenges. Okay, what grading you're talking about? How you're going to uh, how you're going to change that gradation? So what? So you have to understand like when you're talking about the graded junction, what exactly that means. You're saying P type to the N type. Okay, we will just make these changes, not as a abruptly, but maybe you're going to change the concentration on a linear fashion, maybe, and or maybe some number you have used. So maintaining that differences, that's going to be very difficult. Like okay, uh, that gradation, maintaining that particular part, that's going to be little bit different. Yes, so that's what I'm saying, Sri Lakshmi. It's not that easy. See, it's very easy to do 0 1 when it comes to the fabrication. Like okay, here I'm going to do the P, here I'm going to talk about and, because in one area you're going to do this, in another area you're going to do this, and if there is any problem, it's going to be at a junction, and you will just manage that particular part. But when you're talking about like okay, you're going to do certain variation, not the variations are continuously, you're going to maintain this particular slope, I would say, in terms of your composition and all. Then uh, mathematically, it looks very easy, but from the fabrication point of view, it's very difficult. It's not that easy. I would say in that particular way, it's not that easy. Yes, from the simulation point of view, from the concept point of view, that maybe you will say like, okay, it will have less disadvantage. But yes, there are other complexity there, and that may be one of the reason. You will see uh, how many devices are with respect to the graded composition structure if you're talking about. So you have to just check that particular part. I hope I have answered your question. Okay. Anything else? Anyone else? Any other question? So, okay, so what is the time? 11:13. Oh, it's almost like 2 hour I'm talking. So let's do one thing. Let's have this documentation part, the next topic, which is related to the documentation. And then after that, if the break we will take after that particular part. It's just a from the documentation is more or less like five slides. Hardly it will take 20-30 minutes. So after that, we will take it. Okay. Yeah. I was just joking. It will take just a few minutes, like 5 minutes or 10 minutes. So now let's talk about in terms of documentation. So now we are talking till now in terms of the different PDK related thing. What is the content there? What is the importance there? So I just try to give you an idea like, okay, in a PDK, what is the content? What is the importance? Why we are talking about the those things? Now the question comes, in terms of the documentation, like, okay, what documentation we are going to do. So from the documentation point of view, in the sense, if you're going to uh, if you're going to design, if you're going to create a PDK, so for that particular PDK, you have to come up with a certain uh, documentation so the other people can understand. So what are the different documents we are talking about? So this is basically in terms of a yeah, either in terms of the PDF. So like a bonding pad rules. So addressing the rules and the guideline for the layout. So you are going to, as a PDK development, as a the Foundry, you have to tell like, okay, these are the different guidelines for pad structures. So obviously the Foundry is going to provide you. So but that's going to be the part of your documentation. Like, okay, when you're going to create the pads, these are the guidelines. Chip finishing instructions. So basically it is going to tell you the requirement of the Foundry. So if you come up with a special type of layout structure, then Foundry is going to tell you, like, okay, this is my requirement. Okay, you have to do all these things. You have to make sure these things are there, because if those requirements, those things are not there in your design before you just uh, pass out to the Foundry, like, just do um, the fabrication a particular part, then what is going to be happen, like from the Foundry point of view, maybe uh, or I would say in a different way, like, okay, you may not be able to get the right data. So maybe finishing, they have certain things like, okay, for this particular structure, things should not be this, but these type of structure should not be at this particular place, or maybe they have certain margins as per their Foundry, as per their machines. Basically, the Foundry is a manufacturing process, and if you just miss that particular part, maybe um, tomorrow you will see, like, okay, your chip is not working. So those chip finishing related thing, that's going to be there. So there has a separate document. Then design rule, we already discussed in terms of a design rule documentation as a part of a PDF. So Foundry is going to provide you in terms of a design document, like, okay, these are the things which you have to follow, these are the recommendation. Now different vendors, the tool specific vendors, maybe they come up and they will say, like, okay, for these things we have created our own verification deck, and these are the things we can verify. But yes, as from the Foundry point of view, these are the things which definitely they have to document. Similarly, design manual PDK devices. So in terms of the devices, if we are talking about, so this is related to our devices, the primitive cells which we are talking about. For those primitive cells, what are the um, how they have created those things in terms of this particular layout is there, they followed this particular rules, this is a layer map file, this is the DRC file. So if you will see the first and these two things are almost same, but in this particular part, this is more on the rule base. Here this is basically on the part of it devices. Then device cross sections. So you will see they will provide you the devices cross sections also. Like, okay, whatever the devices are there, what is the so obviously they cannot provide you the 3D model as it is, but they can tell you, like, okay, this is the the way if you're going to use these particular device after the fabrication, this is going to be there. So those things will be there. I'm not saying people or the Foundry is going to provide the different document for each and every sections. So this is the document information, like, okay, what all different information is present. So I have divided these things in terms of a different information which is present in the document. So it can be the part of a same document, it can be part of a different documents. Electrical parameters. So in terms of, like, okay, your device is there for that particular device, what is the uh, electrical thing. in terms of peak current, RMS current, uh, in terms of the average current. So with this particular dimension, with this particular dielectric constant, with this particular metal, your device can basically have this much of electrical current, uh, or you can say that this much of peak current. This is the peak one. This is basically the current density. So all those things, basically the part of the document, they will mention this particular part. Now, if they're going to mention this particular thing, like, okay, this is a peak current, that means now someone has to verify this thing. So in your circuit, you have designed something. Now, but how you're going to do the current specific simulation? So someone's supposed to tell you like, okay, these are the for this particular dimension, this is the peak current. And then in your circuit, you are going to do this simulation. You're going to do the analysis. So there are the different tools for electrical simulations, and with the help of that it will give you a pictorial form. It will tell you like, okay, this is the place, there is a red, this is the green, this is the yellow. What is this red, green and yellow? Red means like, okay, whatever the value you have defined, or the foundry is defined, like, okay, for this particular unit size, your current density should be less than this. If it is greater than this much of percentage, it will tell you like, okay, this is basically the red. Yellow is like within a particular margin. If it is mentioned in one of the file, like, okay, if the current density is J and the plus minus 10%, that is okay. So that, but yes, plus minus 10%, that means either it is on a higher side we're talking about, like, okay, the plus minus 10% variation. So that is like, okay, yellow. Now the third is a green, like, okay, you're in a safer zone. So in this particular way, we have a uh, basically the map. And in that particular map, it is a hot and a cold map. We just divide with respect to the color. So you can figure out like, okay, in this particular device at this particular section, there is a current density problem. So you have to redraw your circuit. So these are the things, these are the analysis which you can do in your EDA side. Like, okay, if you are using a EDA tool, because they are going to provide you all these things. But if I will ask you like, okay, you have to do these type of analyses in the breadboard, then it's very difficult for you. You can say like, okay, even in that particular case, if you remember, there is a electrical wire. It has a ampere. It has a ampere, like, okay, 2 ampere wire, or whether we are using a 1 ampere wire, or we are using a zero point 0.5 ampere wire. And then there is a concept of a fuse wire, like, okay, if this is going to be, it is going to draw a more current, then our circuit maybe just disconnect from rest of the portion. So similarly here, you don't have those things. And if, let us suppose, if there is a fuse wire, then how you're going to place it later on? The chip is already manufactured, and then if there is anything just not working, then you have to refabricate each and everything. So if you don't want to do the refabrication, what you have to do, you have to check all these things well in advance. How you're going to check it? Someone is going to provide you those numbers, those things, and those who's that particular person. Someone is going to do the research, and who's going to do that particular research? Obviously, you guys are going to do that particular research. So once you will do the research, you will tell the foundry like, okay, for this particular structure, for this particular metal, this is the current density. And then foundry is going to implement those things in their process, and then they will mention in their physical design kit like, okay, we are supporting this type of material, and this type of material as having this much of current density, and it's safe for whether it is safe for your circuit or not. Just do the electrical analysis. So all this particular part is important from that particular angle. Then similarly on a electromigration thing, so electromigration we are discussing from the very first day, like, okay, what is the electromigration part? So I think you can understand like, okay, what is there. Electrostatic, same thing. From the pads and all, if there is any uh, ESD things happen, then how much it is going to affect my chip. So for that, usually have all the documentation and the guidelines are there. Interconnect specification. So in the interconnect capacitance, what is the resistor, capacitors, parasitic excitation? So those things will be there. So now we are not talking in terms of only the devices. We are talking in terms of the wires also. Like okay, if we are connecting one device with another device with respect to a particular interconnect, that means with the help of a particular wire, then what is the resistor and the capacitor or the inductor of that particular wire, and that's going to help you to uh, do the analysis why in your circuit, like okay, now your overall resistor increases, now overall your capacitor increases, the inductor is increased, now let's see what is going to be happen. So that's interconnect specification. Latch up rules. So I think latch up, everyone know what is a latch up. So for that there are certain preventary circuit is there, so that those rules are there. Layer map, we have discussed this thing, like whenever you have to talk between the three different parties, then you have to come up with a certain mapping file. So this is basically the same thing, layer map file. Mask procurement is basically we are talking about in terms of, it is just for your information as a part of a PDK documentation. It is like okay, for mask making, so like before, how should I explain you? So before doing this thing, the fabrication. So before doing the fabrication, it is all about certain database. Like okay, these are the things. Now that particular layer and everything, first we have to use the mask, and that particular mask, with the help of those masks, it's not a single mask going to be it's going to be the different masks, and with the help of those masks we use all these uh, lithography, etching, all those things. So that's the mass procurement. It is going to tell you like, okay, what is their requirement in terms of the PDK layer and the mask. They will also tell you in terms of the matching models, so local process variation and the mismatch issue, I would say. In terms of the noise model, like okay, in a big design, if it is a large signal, maybe you can say like okay, noise is not going to affect a lot, but if it is a small signal, it's going to affect a lot. It is definitely it is going to affect. So, but whether it is affecting or not, you have to do the simulation, you have to do the analysis, and you have to figure out like okay, this much of noise is not affecting me, and if there is more than this particular noise, then I have to use a noise cancellation or the noise removal techniques. So those models Foundry is going to provide you like okay, this is the type of a noise which can be the part of your system with this particular technology as per their as per their analysis or their understanding. P cell, we already discussed like okay, in a PCL what is going to be the interface and how we are going to document that particular part. Then the next is a process control monitor, PCM parameters provided by the founder to define the acceptable process corner for acceptance. It's basically more or less is just like okay, there are certain uh, there are certain corners, the process corners. So for that particular part, they can say like, okay, these are the acceptable process corners. Then the last one is more from the RF point of view, like, okay, what are the different modeling issues in an RF? So few of the modeling issues we will discuss today after the break. So those are few of the modeling issues. Then we are going to talk about and as a part of a document like okay, what are the voltage and the current conditions, That's basically the part of a safe operating area. So in a safe operating area, you can see it does the voltage and current conditions over which the PDK device can be expected to operate. So if I'm saying 5 nano, if I'm saying 5 voltage, maybe your PDK is not going to work with the 5 voltage, it's going to work with the 1 voltage. So that voltage requirement I'm talking about. Spice model we already discussed. It's going to be RF spice models. It's going to be a just say maybe the mixing RF model, spice model. Those things are there. Spice model library. Yes, that's related to the model files which we have discussed in detail. Tape out in section, how we are going to tape out this particular part. So tape out in the sense like, okay, how once everything is done, the circuit is done, you have created your own layout. After that, how you're going to pass it to the fabrication based company. What is the process for those things? So those things are basically the part of our documentation process. Okay, I'm good, I think, till this point. Any question? No questions? So maybe what we can do, we can have a small break, maybe something like 10 minutes or 15 minutes. I don't know what is, how much you want to take it. I'm okay. So if you want me to continue, I can continue also. Or if you want to take a break, then you have to just use this Q&A section. You have to say like, okay, you need a break. So no, nothing is there. That means you don't need a break. Am I right? You want me to continue? I can do that. That's the reason I'm saying. Firoza ma'am, what should we do? Small break or we just continue?
Yes.
Oh, sorry, we can't. Sorry, I can't hear you.
So, can we take a break of 10 minutes? Then we may start again.
We can we can take it, but no one is asking for the break. That's what I'm saying.
Yeah, so the participants are writing now that they need 10 minutes break, sir.
Okay, no problem.
Yeah.
Yeah. Okay. So then maybe what is the time right now? So
So we may
10:35.
reconnect, like we may start again by 11:42.
Okay, 11:42 or 11. Yes. Okay, no problem.
Yeah. Okay. Thank you, sir. So participants, please don't get disconnected. Be connected. Just take a break of 10 minutes and come back by 11:40. Yeah, hello, sir. Punit, sir.
Hi, brother. Yes, I'm here only.
Yeah, yeah. So can we start now?
Yes, I think we can do it. Let's people just
Check with the
write something.
participants.
Yeah.
So participants, are you back from the break? Yes, sir. The participants are there, sir.
Okay, great.
So you may take over. Yes, sir. Thank you.
Okay, great.
Thank you, sir.
Then I will just start in another few seconds. So everyone's like any question, anything want you want to ask right now? Nothing. Okay. Let's see. Okay. Nothing is it. Okay, so what we are going to do it now because this session is till 1:30. So if I have more than 1 hour. Let me see how much I can cover. Okay, so now let's try to understand from the deliverable point of view. So you now you know what is a PDK. You know very well in terms of the documentation, like okay, from the documentation point of view, what different data you will get in a different it is going to be written as a part of a document. Now the question comes when you are going to deliver something, or if you are on the receiver side, if you're going to receive something, or if you're delivering that, if you're going to deliver something, then from that particular angle, how we divide it. So mostly we divide it into two categories, the front and the back end sides. So the front end is basically, you can see here, so these are the primitive devices, the modeling. These are usually we say that, okay, these are the front end side of my PDK, and these are basically all the DRC elements. These are the final thing. So when we are doing the simulation, this much of data. When I'm talking about only the simulation, this much of data is sufficient for me. So there is a transistor, there is a capacitor, resistor, inductor. There are going to be more other devices also. And what you're going to do, you will just keep all those devices, and all those devices you just place. And once you will just place it, connect, you're going to connect with the wire. Now, I'm not saying the metal. I'm not using right now the word metal here. I'm just saying you're going to connect with the wire, which is like a line. And you're going to connect with that, and then you're going to do the simulation and you get a result. So this is basically the front end part of all those things. But now, if I'm talking about the back end side basically now, let us suppose you want to create your own device. You don't want to use these particular devices. You want to create your own device. That's one thing. Or with the help of the devices, you want to create something else, some circuit, like with the help of the wires, if you're talking about. So all those wires, there are the rules for those different layers. There are the rules. There is a in terms of the whole circuit, if we are talking about. So that's basically now we are talking about in terms of the dimensions, we are talking in terms of the geometries, we are talking in terms of the coordinates, where exactly your wire is going to be placed, where exactly your layer is going to be placed. So that comes as a part of your backend side. So all these things, which layer you are using, what is going to be the coordinates, what is going to be the size, if the size is this, then whether that size is as per the Foundry recommendation or not, and if those things are there, then how you're going to provide that particular information to the other people, what is the location of that particular wire, that particular layer, all these things as a part of your backend size. So
anything on the PDK, anything related to that particular part, and to run, to design, to verify those things, whatever the data you need, the standard data, whatever you need, that comes as a part of your backend delivery of your PDK. So if as a circuit simulator, if you're going to do certain black box related simulation, then maybe you don't need this backend side. Just a front end is more than sufficient. But if we are talking about in terms of the designing, then you need all these things. Then maybe the front end may not is required to you. And again, it's the same thing. So if you are developing your own PDK, so tomorrow if you will say like, okay, I can develop my own PDK. What is the problem? It's forget about the only the technology node. Let us suppose you're saying technology related information, the founder related information. Just let me know. I have my own tool and I want to create my own PDK. Yes, you can do that particular part. Do it. No, not a problem. So let us suppose you will say like, okay, I am not going to use any pre-simulated spice model. I'm going to do each and everything myself. So if you're going to do that particular part, is the front end side, you don't need that particular thing. Even the back end, you just need a limited information. You just need only these particular part. So you yourself can design a device. Once you will design it, you will simulate it, you will see the result, and if you think like, okay, this result is as per your requirement, you are going to convert into a P cell, and you will say like, okay, this is now my cell. So you can do all those things provided you have all the information. Now, same like I was just talking about. Maybe you can ask like, okay, why to use a PDK? Can't we design everything as per our requirement? So I think the use of the PDK, I told you like, okay, why there is a use of a PDK? If you want to, if you're interacting with the Foundry, some other Foundry, if you're talking about some other tools, some other vendors, then you definitely need a PDK. But if you have your own tool, like the customized tool I'm talking about, if you have your own Foundry, if your institute, they have their own inbuilt Foundry, so that inbuilt Foundry is going to have their own design rules. So you can do the experiment and you can come up with your own number, and you can design everything as per your requirement also. Why can't we design ourselves as per the Foundry requirement? Because you can design as per the Foundry requirement. No issue. So I'm not saying you cannot design it. If you have the tool, you can do that particular part. Then someone else can design it. Why can't we? Same thing. So someone is doing that PDK designing. So you can do it. So that's the reason I'm saying, if it depends on which side which side of the table you're sitting. Okay. Am I audible now? I think yes. So I'm just saying, which side of the table you're sitting. If you're sitting on a other side where you are using the PDK, then it's a different thing. But if you are on this side where you are developing the PDK, you can develop your own PDK also. It's just a matter of money. If someone else is going to design it, then if they have their own foundry, their own tool, then you have to pay a lot of amount. Why should we depend on someone else for designing the same? Is it necessary to use the PDK? I think I answered all these questions in all my previous slides. So these are the questions which usually people ask uh, when I present. They usually ask it like, okay, why can't we come up with our own PDK? Yes, you can come up, but the question is which tool you are using. If you're going to use a standard tool, then you have to, uh, so they have certain process, and as per their process, it is going to be certain format. Now, if you can come up with those formats, those process, then there is no problem. But if you have your own tool, like nowadays we are talking about a lot of open source tools. If you're talking in that particular way, no problem. You can come up with your own PDK. So there is a open source tool
I'm just working on one of the small, I would say, small version of one open source tool. So in that particular tool, I can write my own uh, design style. I can just write. I can create the template file as per my understanding. I can say like, okay, this is my tool. This is the format which I'm going to follow. So all those things is basically you can do that particular thing. If I want to answer all those questions in a more professional way in terms of the quality, in terms of the profitability, in terms of the productivity, then this is the answer. So like if you want, if I will say like, okay, from the productivity point of view, if you have a PDK, if you are going to use some vendor tool, the Foundry, then it's just like for you, it's just like a jump start. You can easily set up the environment and you can just start a new project. But if it is something which you have to do yourself, it is going to take a lot of time. When it comes to the quality, the manufacturing companies, manufacturing processes, the vendors, they make sure because that everything is as per the quality. So they are going to do a lot of verification. But if you are going to do those particular parts, the same thing you have to do it. If you will not do it, then you you cannot guarantee like okay what's going to be the quality. But they have their own system. Only you are not the one who's going to pay for these particular things. There are a lot of people they're also paying it, so they make sure like okay the quality is there. And because of this particular part, when it comes to the time to the market, if you are doing a experiment, if you are doing a if you will talk about the some thesis, the new devices, if you are talking about some research area, then obviously you will not get those predefined things. Then you have to do yourself because at that particular time, for us, it's not a time to the market. It's all about the the research side. We have to finish that particular thing. But when it comes to the production level, when it comes to the market, you want to launch a particular uh, circuit to the market, then time to market is very important. So all those things should be tightly linked with these things. So on that time to market, let me just give you one example which is like not only for the you TSMC Intel. So if I'm sure like all of you know very well Intel. So there was a time Intel has their own foundry. It has it has its own EDA tools also, and it has its own research related thing. So they were doing the research. They have their own foundry. They are just validating that particular part. They have their own tools. They're doing everything. And then what happened there, in that particular case, they are working on a technology node which is ahead of the other people, other foundries, and they are like taking around 2 to 3 years just to finish each and everything. Even after that, they are ahead of uh, the the thing. So there was a time we usually say like, okay, Intel is working on this particular node, which is still the other organizations. They are just like they are using something which is like Intel have done 5 year before or 3 year before. But just 10 year back when the mobile things come into the picture, we were talking about the tablet, we were talking about the laptops. Intel realized like okay, if Intel has to launch its own product into the market, so uh, Intel cannot go with this approach because in that approach what is going to be happen, they have to do a lot of things their own, everything they have to do it their own, and their cycle time is around for a particular chip, for a particular processor, their cycle, the overall the uh, end-to-end time is around 2 to 3 years. Then they realize like, okay, they cannot do this particular part. And if they are going to change the technology, they cannot wait like, okay, someone should change the foundry. Now someone is going to change their tools also. So for the lower technology node where the things are more complex, yes, money is one of the factor, but yes, Because of that, now what the Intel, the company, there was a time when they have their own tool. Now they are also using the Cadence Synopsys tools. So they are also using the EDA tools, the some other vendors in their areas. They're also using some other foundries. So because it's very difficult to maintain the foundries also from the pricing point of view also, plus from the research point of view also. So they figure out like, okay, from the time to market, from the profitability point of view, it's good. Like, okay, let's outsource this particular part. Some other person, let's do this particular work and we are going to work with them. But yes, even now Intel has a very specific requirement to their vendors, and whether it is a EDA companies, they have a very sometime what happened, they they come up with the different switches, they come up with the different tools which is specific to the Intel. Means no one can have the access of that particular um, version of the tool or that particular feature of that particular tool. So even now, Intel is doing that particular thing. But yes, my point is just to meet the time to the market, they also jump into the third party thing. Like, okay, now the some other EDA tools, the IC or the fabrication thing. So answer of your question, if you have this thing in your mind, why can't we come up with our own thing? These are the things. And if you will say like, okay, you don't want to go with the Intel things, you have enough time, you're doing the research, you're talking in terms of the you're talking in terms of the PSD level or the master level, then yes, you're most welcome. There are a lot of open source PDKs there, open source uh, tools are there. Not even the open source free tools and the free PDKs are also there. So the reason behind that particular part is just to uh, remove this particular monopoly. Like, okay, people are saying that this is a monopoly. Like, okay, these people are doing, these people are charging this much of amount. Yes, agree. But uh, again, they are doing a lot of verification, all those things. So if you're earning something from that particular product, and if you want to beat the market, then you will just go with that. And if it's something for the research point of view, you can come up with your own environment, the tools and the PDK. Now let's talk about the another portion of a PDK, which is like a quality checklist. So when I'm talking about the quality checklist, so till now what you have done, you have created a PDK. Everything is done. And now just few minutes before I've just mentioned like, okay, if you will see here in this particular slide, I have just mentioned the design quality. I was just saying like, okay, the quality and everything is verified by these particular people, and then everything is good. But uh, but there is a but, there is a star. In each and every document, they have certain things. Now, what is that certain things? They said like, okay, maybe they will say like, okay, we are not responsible if there is a something is just failed in between. Or let us suppose if, even if they don't have a star. So think in this way, you as a company, as an organization, uh, not the big company I'm talking about. Let me talk about you people. So let us suppose out of you, there are 15 people, they are doing the PhD work and they spend almost like 2 years, 3 year. Let us suppose you spend the 3 year, and after 3 year, you did certain research and you came up with a certain numbers, simulation, and everything. Like, okay, this is awesome. Now this is a result. And after that, you just ask the foundry people just to fabricate it. They fabricated it, and now you have your own IC. You have your own device, the circuit, and now you want to test it. So that physical device, which I'm just talking about, on which you're working with a certain research thing, and then when you tried it, you figure out it's not working. It's not working the way it was working on the tool, and it is not working. You check each and everything, you figure out like, okay, there is no problem in the tool, there is no problem in the process. You just followed each and everything, still it's not working. You came back, you ask the Foundry, like, okay, it's not working. Foundry said, like, okay, let me just check it. Foundry checked it. ED vendors, they checked it. And then one of the person, one of the organization, they came back and they said, oh, we missed it something. We missed it. So in place of this, anything, just take any particular thing. In place of this, it's supposed to be this thing. And we accept it as our fault. And what best we can do right now, you came up with another circuit. You just fix this particular problem. We are going to tape out free of cost. Or maybe they will give you the very lucrative offer to your organization, like, okay, the next 5 year, everything is free of cost. So as your PhD guide, as your organization, as your college, everything is good. They will say like, yeah, wow. Now next 5 year, all of our fabrication tool, everything is free of cost. But think about you as an individual. So you spend 3 year. Now after that, nothing is working. And then you figure out like, okay, to fix this particular part, again, you have to work for another at least 1.5 year. Now, who's going to give you back that particular 1.5 year? That's also investment. You cannot do anything. And that's the part of the agreement. Like, okay, it's going to be like 200, 300 pages. You can't read a single line where it's mentioned like, okay, we are not going to mess up if something's happened. Everything is free of cost. Maybe somewhere they have mentioned in that particular way. So the important thing is that you as an individual should also understand the quality criteria. So you can ask your foundries, you can ask your vendors, like, okay, what is the quality? Check they have done it. Similarly, if you are creating your PDK, then you should know what is that quality criteria you have to know. So those things I just want to highlight here. So in terms of accuracy and the clarity, enable accurate time domain analysis. So the time domain analysis, you should know, like, okay, whether things are characterized properly or not. All the passive components, characterization related things, analog and RF models, if you're talking about, have we done the high frequency, low frequency with respect to the noise, with respect to the uh, sub-circuit macro model. So all these things you have to see like, okay, whether these things are meeting properly or not. Integration, if you're talking about whether a particular cells is integrated, if there is a P cell, if you're going to integrate with the some other components, whether that is possible or not. So all those thing you have to just check it. When we are talking about the integration, you have to also see whether now we are talking about the signal integrity or not, whether extraction is correct or not. So what is the best way to build a good PDK? It's just like first you just write a specification. What is your requirement? Collect the founder documents. Like, okay, these are the documents. Build a front end kit, then build a backend kit, verify that particular kit, package the kit, and then the support it. So this is basically the PDK thing. So now in this PDK, if you will see what is happening, it's like Foundry is providing its own document, vendors are providing their own tool, but rest of the part you are doing that particular thing. So you or maybe someone else is doing that particular thing. So they are following a particular process. Like, okay, this is the process. So in this particular process, if you are building a design kit, then you have to check it whether everything is documented, verified correctly or not. Or if someone else did it, at least you should know this particular process. And in that particular process, they're going to be a certain checklist. See, everywhere we are talking about the human. So maybe if you are a PDK development, there are the 10-member team. If one person is going to screwed up, then at least you should be able to, someone else should be able to capture that particular part. So what happened, like we have certain checklists in a PDK development, and in that then we have the So basically in the form of a documentation, in the form of the checklist, what we have done it, like what manual we are talking about, what is the version of that. So design manual, if you are talking about, we are talking about in terms of the electrical parameters, what are the different electrical parameters we have checked, what are the design rules, spice models. See here you can see the documentation number, section, revision date, everything supposed to be captured here. It should not be like, okay, someone created a model file and they did the simulation on a some previous version. After that, the Foundry changed its on some process. Something has changed thing. Now, if those things are changed, so some data you are using of a latest version, some data you are using on a previous version. Now, if this checklist is there, at least it can save you also. It can save the foundry, it can save the vendors also. They can say like, okay, you are using this particular version, and we have clearly mentioned in one of our document, like, okay, these are the versions are compatible with each other. So this is basically that's what I'm just saying. You should know this particular part. Then in terms of the noise models, what all the different noise model we are talking about, the matching models, ESD guidelines, DRC, LVS, parasitic layer map, everything we are talking in terms of the document numbers. We are talking about in terms of the title, sections, revision. We are talking about each and everything. Vendors tools, what are the different tools we have used? What version we have used? What is the version date we are talking about? So whether it is a simulation, it is a circuit simulation type, whether it's layout editor. So it should not be like your one particular version is not compatible with the synopsis, a particular tool and the version. So same thing. So everything's supposed to be as a part of a checklist. So like from the device point of view, just take one example. Like, okay, if you're talking about the MOS, so NMOS, PMOS, LV, THVT, we're talking about the thick oxide, floating gate. So now here we are talking about what are the different types of devices we are supporting here. BJT, what type of devices we are supporting, diode, capacitor, resistor. So at least by seeing this checklist, by seeing this documentation, it's very easy for you to say like, okay, this particular process, this particular version, I'm going to use it. And that's a one thing. So it is going to help you to do the um, uh, selection of a particular foundry, particular tool set, particular version. Second thing is if this document is there, someone has to create this document. So that is basically the part of a checklist. Like, okay, when you're going to provide, you should provide all these information as a part of your PDK. Like, okay, these are the things. So this is basically the to build a PDK. It's not just like you just build one thing and done. It's also important whether it is a compatible with the other versions or not, what version you are talking about. So usually things usually come in this particular fashion. So device table test performed. So you will see once the previous checklist, we usually come up with this type of table like, okay, these are my device name, model name, and then any what is the terminal symbol, LVT, HVT, what is present, what is not present. So this cross doesn't mean it is not present. Basically, this cross, at least in this particular example, may mention like, okay, so tick 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 tick, yes 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 yes. So these crosses basically yes exist. So if there is something blank, that means that's not there. Okay, so that's all. Till now our PDK part, like process development kit, and anyone have any question related to this, just let me know, and after that we will discuss this 5G implementation, uh, some challenges in our 5G. So maybe that packaging part, maybe we will skip, or maybe we will just finish in a maybe the 5 minute session. But yes, here it will take some time, some more time. Any question? Some I'm just waiting if any one of you have any question. Just take 2 minutes. Just let me know. Uh, okay. No questions. Great. Maybe most of you have joined using laptop. I think that may be one of the reasons you guys are not asking. Okay. So there is an option like okay, we can figure out how many of the people are paying attention right now. So I can see like most of the people they are not paying even attention. They did it and switch on and then done. Okay, then let's do this thing. So till now, what we have discussed in terms of the PDK part, like okay, the what is the content of a PDK. Now let's try to understand couple of challenges in terms of the design, in terms of the design a semiconductor if you are going to design it. Like um, we have discussed in first or second sessions, first or second day, we have discussed about this uh, 5G thing. We were talking about the millimeter wave radio systems. So what is basically the 5G is we're talking about is the next generation cellular communication system if you're talking about. But a few days back, I was just reading some articles or so people were also talking about the 6G. I was just thinking like, okay, 5G still not implemented correctly, but people started talking about the 6G also. What basically we're talking about is basically in terms of the millimeter waves, we are talking about the frequency band, like okay, this is going to be our frequency band. But if you're talking about the millimeter waves frequency band, and if you're talking about the previous application, so like satellite communication, we were using the millimeter waves in the satellite communication, the remote sensing, military appliances, and the radar application. So we were using that particular part. So if you remember, like in a uh, older days, if you have seen some uh, devices like maybe in the movies or somewhere, or maybe if you get a chance to visit a even in case of a Indian some military uh, space, I would say military area, then you will see in the older days what happened. There is the device size is too huge. So for the communication, what there is a maybe there may be a guy who's holding a very big set of communication device just to do the communication to the base station. And so that what I'm just trying to tell you, like, okay, in the past also there was there were applications, and those applications are mostly related to the military and the radar things we are talking about, the satellite communication we are talking about. Now, the same type of things, similarly, I would say on a different frequency band, we are trying to do it in a very small size. So, like that time, devices were huge. Now, we are trying to reduce the size of the devices. Now, why there was like in the radio system, why the size was huge is because of the bulky and the power hungry devices. So when we are talking about the power hungry devices, so obviously you will have a big power source. So you will have a power amplifier, noise, low noise amplification, the mixture, antenna, all these things, and you can understand like okay, if the device is if the device size is huge, so big, it's going to take a lot of power. Now, what researcher like you guys figure out like okay, why can't we just reduce the size? The moment you're going to reduce it, the size, but the application is same, but you're reducing the size of those particular device, then challenges are going to increase. Then you came up and you said like, okay, now I'm going to fabricate, I'm going to reduce it in such a way, in such until that particular extent, like everything is going to be the part of a small chip, very small chip. And then we are talking about the power amplifiers as a part of a semiconductor sites. So now if you're talking about the power amplifier in a case of a semiconductor side, then definitely if you're thinking it's very easy, it's not that easy. So there are going to be a lot of challenges. So we will so today's session I'm not going to discuss too much in detail. It's like we have already discussed couple of things um, there in the starting sessions. But here I'm just giving an idea like, okay, what are those challenges? So, like one of the challenge, if you will see the challenges like propagation related challenge of a millimeter wave frequency. In a how it is going to affect my design, the if you're talking from the VLSI technology point of view. So you have to understand those things, the passive component and how you're going to design those. So resistor, capacitor, inductor, those components. Till now, we're talking about the physical discrete component. Now, if you want to fabricate that particular part as a semiconductor, obviously some challenges will be there. And then the way we discussed yesterday in terms of the technology, it's a CMOS technology. If we are talking about the FinFET technology, if we are talking about the uh, BJT technology, BiCMOS technology. So all those things. So if you're going to do the modeling, basically, so how you're going to do that particular modeling. So that the PDK is basically the modeling of that particular part. How you're going to model it, how you're going to place it there, how you're going to fabricate it there. All these things as a part of a design challenges. I'm just saying. Now, in terms of the research community, people are basically uh, the people know more than me here because from the last couple of years, not couple of years, it's like almost like last 1 decade. I'm not working directly as a communication side, but yes, you guys are working in a communication side. So this just to give an idea, like okay, how the research community is working. Like there are the before 2000, there are very we were using these type of radar mechanism. Like okay, some automotive radar by the Mercedes and all. They were using this particular part. But when it comes to our laptops, when it comes to our the television. So if you will see in 2000, 2010, the research community, they were working around this particular part. The second part, I'm just talking about this particular thing, how the receiver is going to be there, what is the frequency of that particular thing, how the millimeter wave silicon technology. So you will see the way the things are evolving. Like in 2001, they came up with the 60 gigahertz unlicensed is used, and they came up with the um, 2009, there is a IEEE standard on those protocols are there, and then we usually talk in that particular way. Nowadays, after 2010, what is happening, and then 2020, after 2020, what is happening? Then we came up with this mobile thing, mobile broadband systems, and then we were talking about the 5G thing. So 5G is in production 2020 onward, but we were talking about the 5G for the last almost like 10 years. So from the research community point of view, we were doing this thing since long, and uh, how the cellular implementation point of view, like okay, they are going to be the small cells, they are going to be the millimeter waves. What are their challenges are there in terms of the refraction, in terms of the reflection, what all different things are there when it comes to the transmissions, when it comes to the transceivers, how things are going to be changed. So all those things you guys are doing, and you, when I'm saying the research community, I'm talking about. Now, in terms of the challenges, if we will talk about that, what are the challenges in terms of EM challenges? Let's talk about those challenges in terms of attenuation, penetration, reflection. These are three important challenges, I would say. These are the challenges when it comes to the 5G. So it's like one of my friend, he's in HP right now, and we were discussing. So one of the hot topic between we both is he's a 5G guy. So he shifted like one, I think 1.5 year back in the 5G group, and from that particular day, we usually discuss in terms of the hardware perspective, although you can say the not the hardware, sorry, the software perspective, like infra related thing, like okay, how they are going to manage, they are going to challenge those things, that once the data will come, and the encryption, decryption, how they are going to do it. So all those things we usually discuss with, I usually discuss with him. But the hardware side, yes, so he don't have much idea about the hardware, but I have an idea about the little bit about the those things. So what I'm just trying to tell you, the challenges are not only on the hardware side, but on the software side also. And when the data will come, how it is going to be there. So these penetration, reflection, these are basically because of the environmental condition. So one of the important thing is you have to understand we are talking about the smaller wavelength. Now, if the smaller wavelengths are there, then it's if you're talking about the penetrating a particular material, if you're talking about in terms of the diffraction because of uh, particles in our atmosphere. So all these things going to change the things. So in one of my seminar, I gave one example. I'm just going to give the same example once again. Like think think the way the let's take an example of a car, and you just take an example of a um, basically a small stone. Now it depends, like that stone I'm talking about, that is basically let us suppose the normal stone in the environment, and then you have a big car. Now if that stone is going to hit you, or if you're just driving your car very fast, and if that stone is going to hit you, or you just hit that particular stone, it's the same thing. So nothing is going to happen. you have a car, there is a very small stone, and you're just hitting it. Nothing is going to be happen. Or maybe if there is a something, some dent, some scratches will be there. That is manageable. But the moment these two things are comparable in size, so that if your size is, if the size of your car is going to reduce, the moment is going to reduce. That means now you become comparable with that particular stone. Now, when your car is going to hit that particular stone, depending upon the size comparison, so maybe your car can be completely blocked. So if the size of that particular stone is too huge and your car is very small, that means your car cannot move. That's the one thing. Second thing is maybe it's going to destroy your car. Yes, your car can move, but it will just uh, destroy some part of your car. That's a second thing. The third thing is maybe the angle which you have like the collision happen. So you just go somewhere else. So that means now we are talking in terms of the comparable size. So in this particular case, in the 5G, when we are talking about the millimeter waves, the same thing happen. So in our atmosphere, there are a lot of things like we have atmospheric gases, we have the water vapor, we have the rainfall in the rainy season. Now, if you are talking about the uh, signal propagation, so what is going to be happen? Like it can go up to a certain level, and after that it's because of these atmospheric thing, it is going to damp out. Trees obviously big in size, so penetration losses are going to be there. So it's because you cannot penetrate those trees easily. In terms of the building and the structure, even in the 4G also we are facing the similar kind of a problem in a metro cities. If there are 4 or 5 towers are there, it's very difficult. In the 5G is going to be more challenging because there are going to be a lot of losses in terms of the penetration. Wood, clear glasses, furnitures. It's not only outside the building, it is inside the building also. Like okay, these numbers, like okay, every house it has all these things. Now there's going to be a reflection mechanism also of the propagating signal outside the environment, and then again we are talking about um, non-LOS, non-light of sight communication, how you're going to do that particular thing. So these are basically the challenges when we are talking in terms of the millimeter waves. And in these challenges, uh, what people do, they sometimes say like, okay, we are going to increase the strength of the signal. And now if we are going to increase the strength of the signal, then it is going to go to the large distance. So like in a current scenario, if you will see in the 4G and the 3G, the 4G, 2G, what happened there is a tower. Now, if you will see if the tower in the, I would say outskirt of your city, where there's no building or something, there, what happened, the zone which we are talking about, the microcells, the radius of those microcells are huge. Single tower can help just uh, that I would say for the signal, it can broadcast the signal. The signal strength is on a higher side. It can just go till kilometers. But within the city zone, um, there are a lot of health issues also. So you cannot increase the signal strength. When I'm saying the strength, the power, I'm just talking about. Then, and if you will not increase, then it is not going to penetrate. Uh, it is there are the losses. The losses are more, and if you will increase it, there are some other issues are there. So that's the reason if you will say within the city, there are going to be a large number of towers. Outside the city, the number of towers are less. So there are some other reasons also, but yes, I'm just trying to give you an example. Like, okay, this is one of the thing. Now, so those things we have to understand, like, okay, if you're going to implement this thing as a part of a silicon technology in a small devices. Now, we were talking about the power hungry devices, and we are talking about the small chips. In a small chip, how you're going to make sure, like, okay, you're inside the chip, the losses, the strength or the signal power, how you're going to maintain that particular part. So that is something which you can do it with the help of the type of a designing which you're going to do it. So from the fabrication point of view, what type of fabrication you are doing, it depends a lot and how you're going to fabricate it. So in a discrete, it's very easy. You can come up with the inductor, you can come up with an antenna. But in a semiconductor devices, if you're going to do that particular part, so it's very important how you're which design technique you're using. So yesterday also we have discussed a couple of device level thing, like, okay, these are the things we are doing. So in terms of the designing, in terms of the design techniques, it can be in terms of the material which we are using. uh, these are the area where you guys are doing a lot of research, and these are the area people are doing a lot of research. I'm just putting a couple of examples just to give an idea, like, okay, how you're going to scale down a on chip inductor. So that's basically a one of the challenge. So as such, if we will talk about the electromagnetic theory, the large size inductor is required to obtain the desired inductance value. Now, you need a large inductor with a good quality factor. How you're going to design that large within the chip. Now, if we will talk about the chip inductor, like, okay, within the chip, if you're going to come up with a thing, then your quality factor can be poor. So it can, obviously, it's a small size, and there are going to be a huge losses also there. So they're going to be a poor quality factor. So what you have to do, the what the people are doing, they came up with the different designs, and they say, like, okay, we will come up with the different type of inductors, and then there are challenges, like, just put it like three different type of inductors. So this is a square shape inductors. Now this is advantage of this type of this, the least number of sites. So there are only 4 sites we are talking about. It's very easy to design, and it gives a high inductor value. So you can just go just like this. You just go in that particular way. In the square is square, you can just draw it from the one point to the another point, and you can increase it till any level. But the problem with this is the low quality factor. It is not going to give you a very good quality factor because there are a lot of losses are there. Then people said, like, okay, if that is the thing, let's do one thing. We will go with these type of things. Now here the losses are less and the quality factor is good. And again, this is also uh, it can also give a high inductance value. But the problem with this type of inductor is this is basically the circular implementation which we are saying, how you're going to do the layout, how you're going to design it. So sorry, when I'm saying the designing, and in the sense fabrication point of view, it's very easy to fabricate such type of inductor. It's nearly, I would say, very difficult, very difficult to lay out a circular, 100% circular. It's very difficult at that particular scenario. But yes, this is one of the ideal solution, I would say. So then people came up with a third solution, and that is a octagonal solution. So they came up with this particular solution, which is, if you will see the A and a C, it is a mixed one. It is almost a circular in nature, and it is easy to design also. So these type of things, like, okay, one, two, three, all these type of things, this is basically come up when you uh, different design they came up when you knew what is the challenges. So these are the challenges, and then you figure out, like, okay, in this particular fashion we can create our own inductor. So once we are talking about the designing, the second thing is how you're going to optimize the thing. So what is going to be the width of the inductor? What is going to be the inner radius? What is going to be the number of turns? What is going to be the track spacing? All those things are very, very, very important. So if from the PDK point of view, if I will talk about, from the PDK, if I will give you inductor, and if I will say like, okay, this is the primitive cells. This is basically the one of the uh, uh, inductor thing. Now in this particular part, if you want to customize it, if you want to make certain changes, so like I said, track width of the inductor, maybe that's something in my cell I cannot give you the flexibility, because that's something if I will make it, if I will give you that flexibility, that's a problem. Maybe inner radius, because it's a pre-designed, I will not tell you like, okay, what is going to be the inner radius. Number of turns, but yes, the number of turns is a something which I can tell you like, okay, this is the thing which you can use it. This is the number of turn. You, if you want to increase it, you want to customize it, you can customize that particular part. And because you want to simulate it, and in for that particular simulation, you can use my symbol, my inductor with the number of turns. And the when you're going to fabricate it, you can make those changes. Now, if you want to design your inductor, at least I can tell you like, okay, if you want to design it, no problem. You can define the track width, you can define the track spacing, you can define the inner radius, you can define the number of turns, and you can create your own inductor. In that particular case, you have to follow certain guidelines provided by the foundry, because what the foundry is saying there should be the minimum width of a particular layer. That means your track width, that is one factor, you cannot go minimum, certain minimum value. You have to be more than that particular value. Second, the track spacing between the two wires, you cannot say like, okay, I can have any spacing, whatever be the number of turns. Obviously, maybe I don't see any reason they are going to provide you the number of turns. You can go till any level. So they are not going to give you any control on that. But at least the track is, at least the inner radius, they can tell you, okay, not less than this. More than this, we can create any point of time. So this is the relationship, how you're going to come up with the PDK development, how you're going to design your device, how that is going to connect with your circuit thing. So until and unless you don't know the design challenges, until unless you don't know um, uh, the, the side effect of different designs, it's very, very difficult for you to figure out like, okay, um why we are not getting this particular option. Maybe tomorrow you will say like and you will come up and you will say like, okay, this is something we are not getting. Why can't we do this thing in this particular fashion? So for this, for all those things, why we are not getting those things, I think you have to just go back and you have to just see like, okay, we can do in this particular way. So that's the optimization, how you're going to optimize that particular part. So you can see some other optimization technique. So here you can see, if this is my inductor, in this particular inductor, if you want to do certain shielding, this is going to be the shielding thing. There is a certain other form of inductor. Then this is a another spiral one, like, okay, this is a one layer. Then with the help of the VR, then we can go in the second layer, like metal one, metal two, metal three. We can go till this particular thing. So again, this is the optimization. This is basically the different designing style, I would say. Now this is the pictorial thing. This is what we are talking about, like on a pen paper. Okay, you came up with this. What about this particular part? This is basically in terms of the cross section thing. How the from the PDK point of view, from the design point of view, from the foundry point of view, what all the different things you need to design these type of inductors. Like they're going to the substrate, they're going to the oxide. Then we were talking about the metal one, metal two, metal three. We are talking about the VR1, VR2. Then what is the minimum width? What is the thickness? So here you can see there are certain if I will give you this particular picture, there are certain parameters which are defined by the foundries. There are certain parameters which is something you cannot change. Like here, you cannot change the thickness of metal one. You cannot change the distance or the I would say this vertical distance between metal 1 metal 2. You cannot change the dielectric which you are going to use it here. You can here you can see this is a metal 2, this is a metal 3. Metal 3 thickness is more, metal 3 width is more. So minimum width you can control. That minimum width you cannot control. More than that you can control. So if your requirement is like, okay, you cannot go more than this particular width, because if you will go, it's not going to solve your problem. That specification is not going to meet. Then whatever you're going to design, you have to design with this particular metal only. You have to design with respect to the metal one only. But if you are okay in your design with the metal one, metal two, metal three, so this stack information is required to you, and then you can say like, okay, this much portion with the metal one, this much portion with metal two, and this much portion with the metal three, and then you are going to simulate it accordingly. Like, okay, this is my design. Now I'm going to simulate it and I figure out like, okay, what is going to be my final inductance value. And to design this particular part, you need these informations. What is the minimum width? Now, what is the thickness? On these thickness, on these things, if there are any variations, foundry variations. Remember, I have discussed about certain variations like plus minus 10 variation, plus minus 10%. I've also mentioned like, okay, if you're going to change your width, how it is going to affect your spacing. If you're going to change your width and spacing, is it going to affect your thickness or not? So all these things, when you will see, if you will receive from the foundry, how they will come up, they have done this simulation and then they are going to provide you. And if tomorrow, if you come up with some other primitive cells which is not defined by the foundry, which is not created by the foundry, then you have to take care about all these things. Like, okay, I'm going to make these changes. This is going to be happen, and then maybe you will say, like, okay, this is my primitive cells. I did everything. So this is a something is a now my inductor of this particular specification with respect to this particular technology, and this is 2x, 3x, 4x, or this is the performance of that particular inductor. So these type of things, these are the things as such nowadays people have done it. So if you will see certain standard document, you can easily figure out like, okay, which design is better solution for you. But just in case if you want to do certain research, there are still a lot of uh, areas where you can just work out. On a similar note, let's talk about a little bit on the transmission lines. So if you're talking about the communication, then we cannot skip the transmission part. So this RF transmission lines, basically, as you know, like, okay, depending upon which particular structure we are using. So there are two different structures. We're going to talk a little bit about. One is a microstrip and another is a coplanar waveguide. And microstrip is like we implement it's like this is going to be my top metal, which is through which we are going to propagate our signal. So this was the metal one. So we are going to propagate through this. So my signal is going to be this, and the ground is going to the substrate line. So this black one, which is you're seeing here, this is basically my ground line. So this is the signal, this is the return path, you can say. So this is a micro strip. When you're talking about the coplanar guide, CPW, if you're talking about, then you can see here, uh, this is my metal one. through which the signal is going to propagate, and these are two are going to be considered as the ground. So this is the ground line, this is the ground line, this is signal line. So this is basically the coplanar. Within a same plane, we are creating our waveguide. Here we are talking about the single line. Both have their own advantage, both have their own disadvantage also. Like here, if you will talk about the advantage, the best part is like you're just using to for a one transmission line, this much is the area you are using right now, because this is a ground, this is the area, and you can just, and the signal can travel through this thing. Next to this, maybe you can come up with another transmission line. The signal is going to flow through that particular one. But this disadvantage of this particular part is, if you will see the distance between metal one and the ground, that is fixed. This thing, that means this particular part I'm talking about. This is the ground line, and this is the uh, our signal line. So between these two, the distance, that is constant. You cannot play with this particular number. But when we are talking about these type of coplanar waveguides, so then you can see now as a designer you have control. In this particular case, as a designer, you don't have any control because you cannot change the substrate. Now, if you want to do the simulation, if you want to do anything, any modeling, you have to, you are going to work on this particular part only with this particular distance. And then if there is a variation in the substrate, you have to consider those variations also. If there is a if there is a something in terms of the manufacturing variation of this, that is again you have to consider those things. So as a designer, you cannot fix certain things here. In a coplanar, the best part is everything is here in a designer control. You can change the distance between the signal wire and the ground line also. This, if you just increase it, then you can just make it. You can increase the spacing also. If you want to decrease it, obviously the RC rule you have to check it, and but you can do in that particular way also. You have the flexibility, but other side of this flexibility is you are using a more area. Then you can see for this you have to use these two also, because you have to shield this particular wire from the both the side. So in this particular case, you are using for the same, you are using the 3 times almost, if you will talk in that particular way. This is just to give an idea, like, okay, the cross section, this is a signal wire, this is a ground, the same thing which I was just talking about, the width, this thickness, and this is basically the height, this is the substrate, and this is the dielectric. Now here we cannot change the substrate height. Dielectric constant of this particular substrate, that is also constant. When I'm saying the constant, in the sense like, okay, if this dielectric constant is not suiting you, yeah, as per your calculation, as per your specification, then you don't have any control. Like, okay, I will fix this particular part. Even you don't have any control in terms of some other way. Like, okay, I will make certain changes in the height, and it is going to fix that particular part. You cannot do that particular thing. In terms of signal wire thickness, okay, that is also you cannot change it. Why you cannot change it? Because that is a metal one, and if it is a metal one, then metal one thickness is going to be remain as it is. Width, yes, you can increase the width of the wire, not a problem. So it's basically, this is the cross section, I would say, the way micro strip lines are there. In terms of limitations, I said the same thing, is a close proximity of the signal plane, like ground plane is very close to this. Because of that, it is going to be the high capacitive quality factor, sorry, or small inductor. Maybe you can say like, okay, Puneet, I'm not going to use with the metal one, I'm going to use a metal 2 or the metal 3. Yes, you can do that particular part, not a problem. But again, the important thing is if you're going to use that particular thing, it is going to decrease my capacitance. But is it a only solution or is there some other solution? We will discuss that particular part in the next slide. Like, okay, what is it? Co the the other solution of this coplanar waveguide. Now, for this particular thing, there are a couple of things like people were talking about the BIMOS process. They came up, they said like, okay, why can't we increase the length of our stripe? And if we will increase the length of our stripe, maybe we can make certain changes. But the thing is like once you fabricate it, then how you're going to make those changes. So for that, what happened? There are some papers I was checking in that particular paper. We were talking about certain solutions. They were saying, like, okay, we are going to use certain pi CMOS process. We are going to use certain switches there. So transistor switches we are going to use. And with the help of these transistor switches, we can increase the length of my transmission line. So it's not like once the transmission line is fabricated, then we cannot make those changes. We can change, we can program our the length of our uh, microstripes also. This is basically they were saying in that particular way. I'm not sure like okay how they were able to do it, but yes, when they did the simulation, they showed a good result. Like okay, this is what we can do it. Now remember, this is something they were able to do it with the help of the third party PDK. A third party PDK in the sense they haven't developed those PDK, some other tool, some tool from the vendor, and then the PDK. They use this thing, they simulate this thing, and they say like, okay, it is a workable solution. So these type of research, these type of things you can also do on your side when it comes to the optimization, when it comes to the solution of a particular problem. Now, CPW with the bottom ground, this is say one more thing. So we were talking about the ground signal and the ground. We were talking about the height, thickness. So here, one more thing, and that is a one more ground plate. Now this is a ground plate. This is a ground. This is a ground. This is a signal plate. So it is now in this particular case, what is happening as per our understanding, initially CPW is just like a two ground plane surrounding a signal wire. But in this particular case, what we are doing, we are saying like there's a one more ground here. And here you can see like, okay, on what are the different parameters uh, uh, from the dependency point of view. There is a dielectric constant here. And then we are talking about the dielectric constant at this particular place between ground and the signal. Then what is the width width of this particular signal? What is the width of this particular thing? And then when it comes to the you can say the thickness of this signal, width of this signal wire, and the height between the signal and ground signal and the signal and the ground wire. So these are the factors on which these things has a dependency. Now, out of these things, you know very well from the PDK point of view, from the technology point of view, below certain spacing, you cannot decrease it. Below certain thickness, basically thickness, you cannot change it. Dielectric constant here and here, you cannot change it. But yes, you can increase the space. Dielectric constant in this particular place, you cannot change it. The height, you cannot change it. So there are a lot of things which you cannot change, but yes, still whatever you have, you can change. That is enough for you. Now, uh, that's the reason like why we are referring CPW because it provide a better isolation when it comes to the microstripes, when it comes to the supporting point of view, when it comes to the the ground strength, if you are talking about, it is easy to do that particular part. You can reduce the crosstalk also, because in the microstripe is basically there is a single wire. There can be a noise or the crosstalk from the adjacent wire. But in this particular case, you're already shielding it, so you can easily reduce the crosstalk. And when it comes to the losses, so it has a low loss at a very high frequency compared to the microstrip. Right? So now, when it comes to the challenges of a 5G, when I was just talking about like the power losses, when we are talking about the signal losses, so now you can see when the way we are designing it at that particular time, we came up with the different solutions, and we are just trying to overcome those particular challenges, at least on a device level. So if my device itself is going to take a huge amount of power, or my device itself is going to take if it will not receive a good quality of signal, that is the biggest problem. So for that, we have to use the optimization technique. We have to work on that particular part. So there are a couple of solutions we are not going to discuss. I think you can just check it later on your our YouTube channel. You can just check it there. One more thing, I think this is going to be my last slide, because the packaging is going to take a lot of time. So we will just finish it up here only. Just some common things which we can do it. Maybe we can just see. Think still we have time. Yeah, let's see. Maybe we can just close it here only. So just to ensure the continuity of your bands, like these type of things, if you're talking about like, okay, how you're going to uh, create this uh, right angle thing. So this right angle thing, sometime this is basically uh, this is one of the solution. Like, okay, people think, okay, in place of this, we will just go in this particular fashion. But uh, uh, you have to understand whether this is something you're going to do it or not. Similarly, people are doing certain mistakes when like this portion. So like you can see the signal is coming, then they are going to reduce the width of the wire. Now here, same thing they are doing in that particular part. So same same here. So all these things you will see like, okay, this is not going to be the good design, I would say. These are the some mistakes which people do it in their layout designing, and because of that, um, when we are talking about these signals, when we are talking about the signal, the quality. So on when we are talking about yes, so I would say the integrity and all other things, that's create a problem there. So best solution is something like this. Like, okay, you should have something like this in place of this, something like this you can propose. Now you have to understand like why this thing is happening, like why these scenarios usually come. So these type of scenarios come when you want to increase the length, and when you or when you are just trying to map two different things, and then there was a stripe, and that was something like with this dimension, there is something like this dimension, then you are just doing certain, just trying to connect those things. So those things you should not do in that particular fashion. You have to make sure like, okay, you should not uh, you should not uh, from the designing point of view, these things should not be allowed. Now there are two ways. Either you just capture this particular part as a PDK, as a verification, or you can capture this thing as a part of a documentation, as a uh, as a recommendation. So depending upon the whether it's whether it can be fabricated or not. If it is not able to, if the foundry is not able to fabricate it, then foundry will tell you like, "Okay, this is not possible." But if you will see, Foundry can easily fabricate this particular part. There is no problem. But Foundry also know if you will do in this particular way, it is not going to give you the good result. So what the Foundry is going to tell you, like, okay, this is the recommendation. Don't do this particular part. So the way the reason I have captured this particular thing, so there are two things in our PDK. One is recommendation, documented recommendation. Like, okay, you just follow this thing. That's the best practice. It will give you the good result. And the second thing is, okay, I'm not able to fabricate this particular part. So all the design rules and everything that is with respect to like whether I'm able to fabricate it or not. But on the basis of their understanding, on the basis of their let's say uh, when they did this these things, they usually add certain recommendation on the basis of their learning. Like, okay, this is going to work out and this is not going to work out. So we, as a part of a PDK, it is very important. Like we should follow, we should see like, okay, what is possible, what is not possible. Possible in the sense what is recommended and what is not recommended. And accordingly, we should design it. Accordingly, we should design our things. Okay, I think I'm good. If any one of you have any questions, I think I have some questions. Maybe I think no. I can't see any question there. Maybe we can stop it here. Today's session, maybe we can just finish it up a little bit early. There is a certain packaging part that is going to take a lot of time now. Firoza ma'am, there?
Yes, sir.
Yeah, so maybe what we can do, we can just close the today's session here only. If people participant have any question, I can just answer that thing. As we will finish it up. I'm almost done.
Yeah, oh, okay, sir. So participants, if you have any query, please put it in the Q&A window. And if anyone want to discuss anything with sir, then please raise your hand. We may unmute you as well. Please let us know. So participants, are you there? Please respond.
So there's the one question. So what is your take on using SIW on the millimeter wave application? Sugaraj, maybe I'm not sure. So we can ask this question tomorrow. We will get answer. So I don't want to share my own view because, like I said, not much expert in these type of applications related things. Okay. Anyone else? So there's one more question like what parameter make difference in choice of transistor for analog and RF? So So it is more or less you're talking about in terms of the difference between the analog transistor and the RF uh, transistor. So let me tell you like in a very the list of the parameters in place of a list of the parameters. If you understand like okay, what is the difference in terms of the analog and the RF? So as such, on a basically what is the RF is radio frequency if you are talking about the frequency basically on those frequency. So everything is related to the frequency frequency related thing. So in in analog, maybe you can say like okay, I'm just talking about a very low frequency devices, maybe you can just talk in that particular way. But when it comes to the RF, there is a specific band. Within that particular band, we usually talk about the frequency. We are doing the frequency analysis. So that's the one of the difference. In terms of the device, like the transistor, when it comes to the characterization, when it comes to the modeling, that is the difference. So what parameters you're going to use it. What I will suggest you, what uh, you can just how should I explain you this particular part? So what you can do it like the RF devices. So if you have an idea about the RF devices, if you just pull up the RF devices and just see what parameters you can change there. So I'm just talking from the device point of view. I'm just talking from the modeling point of view. Then you will get the right answer. I can't give you right now in terms of A, B, C, D, 1, 2, 3, 4. Like, okay, these are the parameters is going to be different in terms of the analog and the RF thing, but most of the parameters are going to be different in terms of the related to the frequency, like, okay, how they're going to check that particular part. Yes, so in a cadence, we have a separate uh, RF MOS. So in terms of the uh, the two licenses, in terms of the MOS, in terms of even the technology point of view, if you will talk about. So see, in analog, in RF, if I will say a technology point of view, I worked on a up to certain technology for the all the communication related thing. And when it comes to the analog, it is like you can just go in any technology node. Even I can say like again 2 or 3 nanometer also have the analog devices. But RF, we cannot go. At least I haven't worked in a that much of lower technology node. Is even for the RF, we have to talk about. We usually talk about in terms of the higher technology node. So that's my experience. Okay. Anyone else? I think no. Yes. Yeah, I think Firoza ma'am, everyone is done.
Yes, sir, there are no more questions. So, sir, if you permit, then we may end the session for today.
Yes, please.
Yeah, thank you, sir, for the informative session, and thank you all the participants and the coordinators who have joined. Thank you all. And participants, please know that tomorrow there will be a second MCQ that is scheduled from 1 p.m. So please be prepared for that. And all the details regarding the MCQ are available on Drive. And the course material, the daily on daily basis, the slides are also being uploaded on Drive. So please keep checking the Drive link on regular basis. So thank you, Puneet sir.
Thank you. Thanks a lot, everyone. Bye bye.
And bye, sir. And so we'll be closing the link. So you may start disconnecting. Thank you.